It's echoing, please check. Huh? It's echoing, please check the sounds. Yeah.
We muted it.
Is it okay? Yes.
We're recording it.
So I'll talk in that.
एडमिट भी आप ही को करना पड़ेगा सो एडमिट के लिए हम दूसरा सिस्टम
ओपन बट दैट काम
Got it. Start. It's already 9. We should start. We should get going. Good morning, everybody. So we start because people will keep joining. So on behalf of the organizing committee of the Indian Quaternary Congress, IQC 2022, I welcome you all to the day 2 of the Congress. I welcome Professor Peter D. Clift and thank him to have accepted our invitation to deliver a keynote. I welcome all the honorary members of AOQR, all participants and colleagues and friends who are linked here today in this virtual platform to listen to the second talk by a legend, Professor Peter Clift. Professor Clift is currently... Hello, am I audible?
Yes, please, go ahead.
Professor Clift is currently Charles D. McCord Professor of Petroleum Geology at Louisiana State University. He is a marine geologist and geophysicist. He specializes in geology of Asia and the Western Pacific.
Can you ask everybody to mute their microphones?
It's a request. Please mute the microphones, and I request the committee, technical committee, to please auto-mute everybody except the speaker. Thank you. Peter is a bachelor's and master's from University of Oxford in geology and a PhD from University of Edinburgh and BSc from, again, University of Oxford in 2014. Professor Clift has worked for the Woods Hole Oceanographic Institution as a research scientist from 1995 to 2004. He was a scientist with the ocean drilling program at Texas A&M University from 1993 to 1995 and was a research fellow at the University of Edinburgh sponsored by the BP and the Royal Society of Edinburgh. He was a professor at the University of Aberdeen from 2004 to 2012, and currently he is at Louisiana State University, which he joined in 2012. To his credit are several awards and honors, to name some. He's a GSA Fellow, Murchison Prize of Geological Society of London. He's a Fellow of the Hans Institute of Advanced Studies, Germany, Visiting Professor, Chinese Academy of Sciences, Humboldt Fellow, and several more. Professor Clift is a geologist who applies marine geophysical, geochemical, and classical geological methods to understand the history of geological basins. He works on understanding the relationship between mountain building in the Himalaya and the Tibetan Plateau and the intensification of the Asian monsoon. Professor Clift has worked on the evolution of Indus River, sediment records of the South China Sea, and is also involved with efforts to have the integrated ocean drilling program to collect samples from the Asian marginal seas for monsoon studies. Recently, last year, he organized this monsoon seminar series with weekly talks throughout the year, and it was a very popular science series. Professor Clift also works with the tectonic and the nature of mass recycling in subduction zones. Most recently, he has developed interest in understanding environmental change driven by climate change in Asia since the LGM and the potential impacts on early human societies. Professor Clift has published his work widely and has more than 19,000 citations. With these words, I can go on and on, but I have to stop. With these words, I welcome you, Professor, and I invite you to deliver the keynote on a very interesting topic, monsoon influences on erosion and sediment transport in the Indus River catchment, Southwest Asia. Over to you, Professor.
Thank you very much for your kind introduction. Can you all hear me okay?
Yeah, yeah, you have to share your screen.
Yep. And
yeah,
1 second. There we go.
Yeah, and you open your presentation. Yeah, fantastic. We see
Okay,
it.
that's good. Okay, so what I'm going to do is talk to you a little bit now about the Indus River and the Quaternary and what effect the changes in climate have had on the production and transport of sediment from the source mountains, this is Dharamsala, down here to the delta and of course into the deep ocean, into the Arabian Sea. And so the work I'm going to show you is based on work done by a variety of students and postdocs, people from the University of Aberdeen in Scotland, and more recently my students here in Louisiana, who continue to work on monsoons. So of course you all know what the monsoon is. It's the seasonal change of the wind patterns in Asia that bring moisture, especially to South Asia, to the Western Ghats and the Himalayan front. And in particular, of course, there's this idea that the monsoon represents something a little different from other parts of the world, where normally speaking, the greatest heating would be at the equator and where the precipitation occurs and the dry air subsides in the mid-latitude. But of course, that's reversed in South Asia, where the greatest heating is over the Indian subcontinent. So what that means is that we have a very seasonal and a very concentrated rainfall. This map here shows the Indus catchment in Southwest Asia, and of course the dark blue colors are showing the concentration of precipitation along the range front, especially in the lesser Himalayas in the present day. And you can see how dry it is on the Tibetan Plateau, as well as, of course, in the southern parts of the drainage here in Sindh and bits of Baluchistan. And we know that this area is also affected by winter precipitation brought by the westerly jet. And in the winter, it's displaced south of the Tibetan Plateau and brings in moisture here, especially in bits of Pakistan and in northwest India. So this is the series of little catchments that I want to talk to you about. Each of these little basins contributes to the overall flux into the Indus River, and it's bringing, of course, material from a variety of source areas here, spanning from the Hindu Kush, the Karakoram, bits of the edge of the Tibet Plateau, particularly in Ladakh, and of course the Himalaya, lesser and greater Himalayas as well. And we're going to think a little bit about how these different types of basins store and release sediment and how that's affected by changes in the monsoon over relatively short time periods, over millennial time periods. And we do know that there's a lot of evidence for sediment storage in the mountains. We know in places like Ladakh, we can see there are lake deposits. This is in Spitok, near Leh, where you have lake deposits along the main course of the Indus River. We have, in many valleys, we see infilling and then incision of fluvial sediments that are filling the valleys, sometimes relatively modest. This is about 25 meters cliff. And then in other places, very large ones here at a place called Pang, on the which is about 250 meters deep, and then also here along the main Indus River, where we have a terrace and incision. So we know that there has been sediment stored and then released. And what I want to understand is, how does the monsoon affect that process? So we can begin to understand this if we know what the age of the terraces is. Here, for example, is a beautiful fluvial terrace, which is now being incised. And if we know what the age of the terrace is and the depth of the incision, we're able to calculate the amount of sediment that's been removed and the timing at when removed. So we're able to try and make a little sediment budget. So in Ladakh, for example, some of these sediment terraces are actually quite old. So for example, here's a very prominent terrace. There's the Indus River here, and a very prominent terrace here, which is actually dated as being quite old, 130,000 years old. So these are, although there's a significant amount of incision here, it took place over a long time period and may not have been a big influence on the sediment load of the river at any one particular time. We do, however, know that some of the lower terraces can be important when we're just thinking about the time since the last glacial maximum. So along the Indus River, we know that the river must have been blocked in places because of these lake deposits here at Spitok and further downstream in this place Ule Tokpo. And you can see here, this is the Indus in Ladakh. There's a very prominent terrace up high here that we don't really know how old it is, but the one down here is essentially about 10,000 years old, 8 to 10,000 years old, and that has been incised by the Indus River. You can see it's actually quite significant. There are some little jeeps driving along the road here. So on the north side of the rain shadow in Zanskar, so we're talking about this region up here on the north side of the Great Himalayas. In the rain shadow, my former student, Tara Janelle, was able to measure and date terraces in this region. And there are older terraces. You can see there's one here at 32,000 years old, but many of them are dating from the early Holocene. For example, here at Renam, you can see a 9,000 year age and an 8,000 year age here, 10,000 year age. Many of them are showing infilling of the valleys, forming these terraces here in the early Holocene. And that subsequently, the valleys are being incised as the Holocene proceeds and the climate gets drier. We also know that there's sediment in other parts of the catchment. So around Nanga Parbat, for example, there is large-scale mass wasting, this landsliding that came down and blocked the Indus in places. And these deposits have been mapped out. And of course, they do contribute to the sediment load on short time periods because the river cuts through these and then releases the material into the downstream. And because we know the age of these landslides and how much has been released and how much is now eroded away, we can make an estimate about their contribution to the net flux to the ocean. Likewise, in the Karakoram, we see large-scale rock avalanches, but also, of course, recycling of material from moraines, from glacial moraines, where the rivers are now cutting through these. And so we can, some of these have been quantified and dated, and we can use the data from the landslides that have been dated to estimate what the total contribution may be. So a lot of these are mass wasting caused by the retreat of the glaciers that had previously buttressed the sides of the valleys. But again, we can use the eroded volumes here to estimate how much material like that has been released since the last glacial maximum. Then on the south side of the Greater Himalaya, again, there are significant terraces along the big rivers. This is it's the Bayas, south of Manali. And then, of course, there was work done by Bodo Buchhagen and friends from Germany who looked at terraces along the Sutlej. And again, a little bit like north of the Sucha, what they saw was that the times of infilling of the river tended to be when infilling of the valley occurred when the monsoon was strong, and that there was incision when the monsoon was weak. And again, the length of the valley and the depth of the incision allows us to estimate how much material has been stored and then released. One of the other major depot centers is also the incision on the floodplain. So we know that the northern part of the Indus floodplain, the big tributaries, not just the Indus, but the Jhelum, the Chenab, the Ravi, the Beas, and to a lesser extent the Sutlej, that we know that they're incising into their floodplains, and this has started about 10,000 years ago, about the same time that we saw for many of the terraces in the mountains as well. The terraces here, the terrace is not very deep, but it is very wide. So these can be 10 or 15 meters deep, and then they span 30, 40, sometimes even 50 kilometers across. So this turns out to be a big sediment source. Yes, you can see here, these are colored in here. These are the incised valleys, which have been scooped out and then recycled since about 10,000 years ago. And we can make an estimate of how much material has been excavated since 10,000 years ago. One of the greater unknowns in this sediment supply process is the role of the tar desert. So because we do have information from OSL ages that show the ages of accretion of the desert. And we know that the river sometimes cuts through the desert, like here in the Nara Valley in Pakistan, where either the Indus or a distributary of the Indus used to cut through the edge of the desert. And of course, up here in Cholistan and northwest India, where we see the remnants of the old Gagahakra River has been recycling sediment out of the desert. We did have some information about where the sediment is coming from. Neodymium isotopes suggest that the greatest source of the material in the tar desert is the Indus Delta itself, or at least the lower reaches, and that this sediment is being transported from the lower reaches into the desert by the summer monsoon winds. It's not coming from the biggest local rivers like the Sutlej. You can see the neodymium isotopes are quite different compared to the dunes. Nonetheless, the potential for sediment storage and recycling in the tar is significant. The volume of sediment that we see in the tar is almost similar to the volumes that we estimate for the Indus Delta during the Holocene as well. So potentially it may be significant. And this is something I'd like to work on more in the future. So you can see these are the sources of eroded sediment into the Indus since the last glacial maximum. And what we've got here is the estimates of the mean and then maximum and minimum. I mean, there is significant uncertainties here, but you can see we're looking like, if we look at all these river terraces in the mountains, floodplains in some of the terraces in the hills towards the west, the Kithar and Suliman ranges, the floodplains are actually probably the single biggest source of sediment, around 650 cubic kilometers. The rock landslides around Nanga Parbat and the Tibet and the Karakoram are a little bit less. Tibet itself is a relatively small part of the total sum. So what we see is that of the amount eroded, the biggest single component would be from the floodplains, and with smaller amounts from these river terraces, and a rather poorly defined amount here from the tar desert. So where does all this sediment go? Well, we do know that some of it is going into cliniforms in the offshore. There's this big eastern cliniform that's prograding out on top of this last glacial maximum surface, the erosion surface on the continental shelf. Towards the west, there's a much smaller cliniform, and that's reflecting the longshore current that's blowing sediment from the river mouth towards the west, maybe even into forming another cliniform here near the run of Kutch. There's also sediment deposited, especially during times of falling sea level at the shelf edge. So we see in Sparker data from surveys on the outer part of the continental shelf, stacked cliniforms. These shelf edge deltas are formed during the falling stage and represent a not insignificant amount of sediment. And then, of course, there's the Indus Canyon itself, and we do realize that this continues to be active even when the sea level rises during the Holocene and at the high stand. And we have a series of cores that run along here, which show continued Holocene deposition, admittedly stronger towards the top, more turbiditic towards the head of the canyon, tailing off as we go down into the deep water. And the fan itself is documented as essentially falling inactive about 10,000 years ago. So we think that what's been happening here, we do have terraces in the canyon too. You can see here these series of flights of terraces mantled now with younger hemipelagic sediments. But we see two forms of sediment flux at the high stand into the canyon, both turbidites that at least go most of the way down, but not all the way to the fan, as well as hemipelagic sediment falling out from plumes of material. And we know that that sediment is being essentially redeposited in real time from the river, a sort of a direct connection on the basis of isotope data. So the Indus River has a lower strontium isotope 8786 value at the glacial and early Holocene times, and it's got higher values since that started about 8,000 years ago. And you can see the Holocene sediments in the canyon pretty much look like the river. They're not mixed really between the two, that they are dominated by essentially direct connection of sediment supply from the river mouth. They're not recycling old material from the canyon. And as I mentioned, the fan itself becomes inactive about 10,000 years ago. We see, or certainly by 8 here. If we look further downstream, though, onto the fan itself, so there are, of course, these major channel levee complexes. These ones were imaged by industrial seismic data, where we see quite thick sequences of channel deposits, and then the overbank, the levees. You can see the scale here. This thing is about 25 kilometers across, and it's about 500 meters thick in places. So these are not constructed in a single low stand. We presume that they're not active at all during sea level high stand, but that we get rapid, significant amount of sediment are deposited in the channel levees during the sea level low stands. And then, of course, further downstream, there are lobe deposits on the submarine fan itself, further out in the main Arabian Basin, as well as in Lakshmi Basin, as drilled by IODP. So again, as I estimated the eroded volumes, you can do the same thing for the deposited volumes. We have sediment here in Sind, under the alluvial plain. We have material in the delta, in the desert itself. We have the sediments of the cliniforms, and as well as a relatively small amount of sediment. This is in the Holocene, right? So very small amounts of sediment in the canyon representing just a fraction. So the total amount deposited is actually quite significant, about 6,000 cubic kilometers, which is actually far more than has been recycled. So if we try and do a little budget, we get something that looks a bit like this. So these are all the different sources of sediment during the Holocene to the Indus River, to the lower reaches. And so this is dominated. 75% of it is coming either out of fresh bedrock erosion or out of glacial moraines, with only small amounts out of the floodplains and very small amounts out of the terraces. No matter how dramatic they look, they're really not a very large volume. So where does the sediment go? Into the alluvial plain, the delta, and those cliniforms, with almost very little in the canyon and nothing in the fan itself. So what's interesting about this is that that means that we have this average sedimentation rate since sort of the end of the glacial time, since about 14,000, with about 1.2 gigatons a year. So that's actually a lot. So in fact, what this means is that if we look at the recent pre-industrial delivery of 250 to 300 million tons or so, or even these higher ones here, that this implies that the rate of delivery was much higher in the past. If the average since 14 was 1.2 gigatons, even these high values here are less than half that. So that suggests that we must have had much higher rates of sediment supply in the early Holocene compared to the late Holocene. And it also suggests that 75% of the sediment that's been deposited in the Holocene is actually coming from fresh erosion of bedrock or moraines. And we can play this game in reverse by looking at the last glacial maximum, because in this case, we know that the sediment during the falling sea level and low stand, it's being deposited at those shelf edge deltas, in the submarine fan lobes, and in the channel levee complexes. So we have quite large volumes are estimated to be deposited at those times. And what's interesting here is that the total, which is not from reworking, is actually relatively modest. And what that means is that only 24% of the sediment deposited during the low stand, like here. So here we can see there is some flux of sediment from the original source terrains, but actually a lot of the sediment is being picked up by incision from the delta and the floodplains, and also, of course, the recycling of sediment out of the cliniforms. And at this point, when the Indus fan itself is being constructed, most of that sediment, 75% or so of the sediment, is not from original sources, but it's being recycled. So the sediment deposited in the fan during the glacial times is actually mostly reworked. It's material that was eroded and deposited during the previous interglacial. So let's have a look about where that sediment is coming from, and we can do that using neodymium isotopes and zircon dating. I don't have a lot of time here today, so I just wanted to show you some data from the zircons, and this works because of the differences between very young grains in places like the Karakoram and in Kohistan compared to older material in the Tethyan and Greater Himalayas, and in the Paleoproterozoic Lesser Himalayas, we get this very distinctive 1.8 billion year peak. So let's just have a look at these. This is a KDE. It's a plot of zircon ages through time. What's interesting to note here is that, so these are old ones. These are 5.7 million and 15 million. You can see, we know they're Indus fan sediments because they have the young characteristics of erosion of material from the Karakoram. You'll note that they don't have many of these lesser Himalayan or even very large greater Himalayan peaks. It is interesting to note that the modern river in the lower reaches near Tata, near the delta, has this very prominent 1.8 billion year peak, which is characteristic of the lesser Himalayas, and that's much smaller in the early Holocene and just after the glacial. And what is interesting to note is that the Indus fan sediments, this one is about 800,000 years old. So this one does have the Paleoproterozoic peaks in it, and it looks like the Indus fan is mostly composed of sediment that is being eroded during the interglacials, not during the glacial times, as we were projecting. This is, I think, what a multi-dimensional scalar diagram. It's a way of comparing the Zircon patterns. And it's interesting to note here that the modern river and the Pleistocene turbidite here actually plot near the Himalayas. These are much more Himalayan compositions, and that the glacial era sediments here, 7,000, 14,000, are plotting closer to the Karakoram. So they're displaced. There's a stronger emphasis on erosion in the Karakoram during glacial times and more Himalayan during interglacial times, presumably because the monsoon is stronger at that time. And we can see that a little bit here. So here are monsoon records from the Kumff cave in Arabia, where we have the strong monsoon in the early Holocene, and at a time with rapid deposition in the delta, and also the deposition of essentially more Karakoram-dominated sediment earlier on, which is then, as that phases out, we see more and more erosion from the lesser Himalayas. So that as the climate change, not only does the composition of the sediment change, but the source of that changes. The climate is controlling where the erosion is taking place. We have to be a little bit careful when using zircons, because it turns out that the Himalayan tributaries are enriched in zircon relative to their the trunk Indus, the mainstream Indus. So if you look at the zircon budget, it looks like a lot of the sediment is probably coming from the Jhelum and the Chenab, and relatively little from these tributaries. In reality, the suspended sediment budget is not quite as heavily biased in that respect. So you can see, this is percentages here. So the Indus is always the big one, but you can see the Jhelum in particular is overestimated by the application of zircon. So we have to be careful. We can try and correct for that, but it's not entirely trivial. So we have attempted to do some unmixing of the sediment sources. These are the different major sources in the to the Indus through time. So here's the modern Indus River, and we did this using two different statistical tests. So what you see here is actually a lot of sediment supply from a variety of sources. The Himalayan, the Tethyan and Greater Himalaya are quite important. Even the outer Lesser Himalaya are quite important. Kohistan and the Karakoram are a little bit lower. But if we go back in time, you can see here that back at 7,000 years ago, the Karakoram is the most important, and at 14,000, it's quite dominant. So what we see is a phasing out of erosion of the Karakoram and a stronger erosion from these Himalayan sources, especially the lesser Himalaya. Okay. So what I want to do is now just sum up, hopefully, what I showed you there. So erosion in the Indus Basin is controlled by monsoon intensity, and the pattern of erosion changes through time, mostly related to the strength and distribution of the rainfall. So the Holocene flux to the ocean is dominated by new erosion, about 75% of it, and about 25% is from recycling from older deposits. Whereas it's the other way around in glacial times, it's only 36% is fresh, and the dominant source, I think that's a misspelling, it should be 26. 70 and then 74% of it would be eroded from glacial stuff. So I didn't talk about this very much, but Nanga Parbat is not a very important source. The Thar Desert, however, may be important, but we don't really know yet. And I'd like to try and work on this more in the future when the pandemic is over and it's easier to do fieldwork again. So of the sources we do know something about, the floodplains appear to be the largest source of recycling, about accounting for up to 11% in the Holocene. And it's interesting also to note that those sediment budgets imply there must have been much higher sediment supply in the early Holocene, more than 1 billion tons a year, compared to much lower in the late Holocene and pre-industrial. And so during the sea level high stand, the sediment is sequestered in the delta and on the shelf, and a little bit of mud and sand, silt gets down into the canyon, but very small volumes. The fan is inactive, and so we see there's, however, very little buffering between the river mouth and the canyon, but only for these very small amounts of material. But there is basically a direct connection there. We shouldn't forget about the shelf edge deltas. They're supplied during the sea level fall. And I think an interesting point here is that the deep sea fan record is, it's all deposited during the low stand, but the material is eroded during the interglacials, during the high stand. So that means you can't take sediment from the Indus fan and correlate it directly with the climate on shore at the time it was deposited, because it's always going to be offset by essentially at least half a glacial cycle. So without further ado, I'm going to stop and I will be happy to take questions. Thank you very much.
Thank you so much, Professor Cliff. This was a real nice journey of the river Indus, right from, the upper reaches to the floodplains, to the delta, to the canyon, and to the, fan. And with so much of quantified data that you showed us, we do have some questions in the chat box. If you see the chat box.
Yes, I see Vimal Singh has a question.
Yeah.
Vimal, what's your question, sir?
Hello, Professor Cliff.
How's it
Interesting talk. My question is that how do we basically look at the tectonics? What is the role of tectonics in this? Like, we know that a lot of these tectonic fluxes could actually be coming due to this tectonic activities. So, so does it get buffered, or how do we see that in such reservoirs?
Well, I think on like a time scale that I was talking about, that it's not terribly significant. I mean, earthquakes must probably result in more landsliding. I think that the tectonics is more important on longer time scale. So I went through it rather quickly, but actually, at 15 million years ago in the mid-Miocene, although the monsoon is strong, a lot of the erosion is then from the Karakoram. So that's the opposite of what we see in recent times. And I think that reflects essentially, that's the solid earth talking to us, that the monsoon can erode, but it mostly erodes things that are being rapidly uplifted. And so I do believe that this tectonics is important. Essentially, the tectonics is also important in guiding where the erosion happens, but the monsoon modulates how much erosion is happening.
Okay, thank you.
But if that's not terribly clear, it's because I'm not entirely sure about that myself.
Okay,
thank you.
Professor Singhvi is here. Please.
Yeah, it's more my ignorance. You are using mostly OSL ages, which essentially date the preservation event.
That's right.
Now, there is a fair amount of sediment that might be bypassed without your preserving it, right? So how do you connect the sediment that is bypassed? Because your story is based on what is available to you.
Yes, that's right.
So how do you account for the sediment that just gets bypassed, and does it affect?
It has, if it's bypassed, it has to be deposited further downstream, and so we know in places like the canyon and the submarine fan that the sediment is not going there during the Holocene. So it can't be bypassed entirely, not all the way into the ocean. you're right. It would be good to do cosmogenic dating as well. When we worked on those Ladakhi terraces, we just didn't have. I didn't have access to that type of technology. So, but yeah, we do have to be careful. But I guess the nearest thing we can do is to try and sample the terraces close to the top, so that we know when the last material was being deposited.
Okay.
Yes, because there could be a time gap between the preservation and the production of sediment. So, do you see a signature of that in your records?
I don't think there is actually. I mean, like in somewhere like in the river terraces in Ladakh and in the Sutlej. I mean, the sources are so close, and the sediment transport times are not that long.
No, I'm looking at the record from the origin to fan, for example, the Indus fan.
Yeah, well, those may be buffered by 100,000 years. I mean, it's possible that sediment that's being eroded at the beginning of a cooling episode does not get recycled until much, much later. That's right.
I'll stop here. We'll talk later because of the other meeting. Thank you for a wonderful talk. Thanks for a wonderful talk.
Thank you.
Thank you for coming.
We could just take one more question from Rajiv, and then because Peter, we have lots of questions for you. Maybe we can just send it to you through mail, and I can.
Absolutely. Yeah. I'm sorry I can't attend the meeting. I just too tired.
Yeah, I know it's too late for you, and thank you for being here at this time of the hour.
I'm going to come back to India as soon as I can.
So, sure. So, so Rajiv,
Peter, I just want to know what is the reason for that anomalous river contribution estimates that you get from the Zircon and the.
That's right. So that's a good. I mean, it must just be the composition of the bedrocks. I mean, I guess what I'm thinking is that there's quite a lot of mafic rock in places like Kohistan and the Karakoram, and a lot of the Himalayan lithologies like the metamorphosed sediments and the leucogranites are just much richer in zircon. It is quite interesting if you go and take some of these sediments and you can analyze for zirconium, and there's in some of them there's 5 or 10 times more zirconium than there is in the trunk Indus. I mean, we do have to look at this more because, and I know people like Eduardo Garzanti don't really approve of people doing this. He wants us to point count them, but not all of us are as good at a microscope as Eduardo. So I like to measure zirconium because it's easily done. I think it's particularly the really old Himalayan rocks, the Proterozoic stuff. I recently measured sediment coming off Nanga Parbat, which I didn't get to talk about here. That's really rich in zircon. In fact, it makes Nanga Parbat even more embarrassing because you would think that the river downstream of such a rich source would be filled with zircons like that, but it's not. I don't really know why not. It's a pretty good big mountain, but but it's compositional, and and they're not all the same. The gelum is actually very enriched.
Okay.
Okay. Okay, thank you, Peter. Thank you for being with us.
Okay.
It was indeed a wonderful.
It's a great pleasure to see some familiar faces.
Thanks to be here for the first IQC, and in the future we'll see you and hear you again.
I'd like to come in person next time.
Yeah, next 2024 in person. Bye-bye from all of us.
I hope so. Okay.
Thank you.
Enjoy the rest of your day.
Thank you so much.
Bye-bye.
Bye. So that was the keynote from Professor Peter Clift, and now we move on to the session. The session, it is on Earth surface processes, and the moderators are myself and my colleague from Wadia Institute of Himalayan Geology, Anil Kumar. So we go directly to the first presentation. Bulbul Mehta, are you there?
Hi, ma'am. I'm here.
Okay, please upload your presentation. So this
Yeah,
is
sure.
a paper by Bulbul Mehta, Ankit Yadav, Sayag Basu, and Anupam Billi. And they would be talking about the characterization of sedimentary organic matter and depositional processes in the Mandavi estuary, Western India, and integrated lipid biomarker, sedimentological, and stable isotope approach. So, yeah. Yeah, Bulbul, please. And I request all of you to please see that, the time is 10 minutes. So 10 minutes, you could finish your presentation and have some discussion. We just go to the next topic. Over to you, Bulbul.
Hi, ma'am. Am I audible to you?
Yes, please go ahead.
Good morning, everyone. Myself, Bulbul Mehta. The topic of my presentation today is characterization of sedimentary organic matter and depositional processes in Mandavi estuary, Western India, and integrated lipid biomarkers, sedimentological and stable isotope approach. So the contents of my talk are motivation, introduction, objectives, methodology, results discussion, and conclusions. So let's talk about motivation first. The motivation behind my study is that, as we know, that estuaries, they are the transitional zones between riverine and marine environments. Also, they receive input from various natural sources by the means of soil litter, vegetation catchment, and anthropogenic sources like oil spillage, trace metal contamination, and various recreational activities. Well, this study is important because various earlier studies dealt with trace metal contamination and physical parameters, but the corroboration of organic matter source characterization and the advancement of pollutant is still absent from this study site. So Mandavi estuary is a tropical estuary, which is located in the west coastline in Goa. And this particular estuary lies between Western Ghats and Arabian Sea. And the study site is covered by mangroves, and it receives its precipitation during southwest monsoon. The approach that I used for my study was based on three proxies, that is biomarkers, isotopes, and sedimentology. So the primary objectives of my study were to understand the various depositional conditions using grain size parameters, to understand the productivity changes using TOC percentage and delta 13C values, to understand the circulation dynamics based on the stable isotope approach, to know the various organic sources, and lastly, to understand the pollution status of the estuary. The sampling technique that I adopted was I used a Van Veen Grab sampler to collect the various surface sediment samples, and the upper, middle, and lower estuary was covered, and the sampling points were total 26, covering the upper, middle, and the lower estuary. Now let's talk about the first proxy, that is grain size. So the grains the sediment was measured from the grain size analyzer, that is Master Sizer 3000. And we can see the results here, that the sand percentage was higher in the lower region, while the silt and clay percentages were higher in the upper region, thereby indicating the high energy conditions here, that is in the lower estuarine, while the calm and low energy conditions in the upper estuarine region. Now let's talk about delta 13C. So TOC percentage and delta 13C per mil, the values were measured using coupled IRMS. And let's talk about results here. So the TOC content was higher in the upper region, and the delta 13C values indicate the accumulation of aquatic productivity. For example, sea grasses or the marine the marine phytoplanktons, they were quite abundant in this region. And C3 plants, basically the terrestrial organic matter was abundant in this region. Also, there was the correlation analysis that was performed between D43, which is de Broca diameter. It is basically grain size parameter, which measures the size of various grains. So higher the D43, higher is the size of the grain. So the correlation analysis was performed between D43 and TOC percentage, and they were inversely correlated with each other, which indicates that higher the grain size, lower is the preservation rate of organic matter. Now let's talk about delta O18. So delta O18 values from the water samples were measured in IRMS, and the results indicate that there were negative values in the upper region and positive values of delta O18 in the lower region, thereby indicating the circulation of fresh water in here and saline water circulations in this region. Now, the next proxy that I used was biomarkers. So biomarkers are basically the organic molecules that are used to understand the various organic sources, and also they are used to understand the environment of deposition in a particular basin. So for the biomarkers, I basically concentrated on the alkanes part, because these are, out of all, these are quite resistant to degradation. And based on NLKs, so various organic sources, for example, algae, bacteria, aquatic plants, terrestrial higher plants, they all have their characteristic carbon chain lengths as shown here. So based on all these carbon chain lengths, various proxies were also calculated. So now firstly, let's talk about the methodology for biomarkers. In this case, we just powder the dried sediments, and the sediment samples, they are extracted using a solvent extractor. And basically, the solvents used here are DCM and methanol in the ratio 93:7. After the solvent extraction is done, the lipid is concentrated in the multivap, and that 0.5 to 1 ml of the concentrated lipid
I'll just interrupt you. You can go to your results, because you have just 3 minutes.
Okay, sure, ma'am. So various proxies were calculated, and let's talk about results here. So the tar values were higher in the upper region, while the P aqueous was higher in the lower region, thereby indicating the high terrestrial organic matter accumulation here and the high aquatic productivity in this region. Also, they were inversely correlated with each other. Now let's talk about the next indices, which is CPI and ACL. So these both proxies were equivalent to 1 in this region, thereby indicating the role of petrogenic source. So petrogenic source basically indicates about the petroleum contamination. Also, the correlation analysis was performed, and they were positively correlated. To further understand the petroleum contamination in the system, various other proxies such as NAR and pristine phytin were also calculated, and they were equivalent to 0 in this region. So, which indicates that again the system, basically the lower estuarine part of the estuary, was highly contaminated from the petroleum. Further, the TIC was also investigated, and we could see here that there was high UCM. So UCM is basically the unresolved complex mixture, and this mixture is observed when it is unresolved by the capillary column of GC. So high UCM is a very reliable tool to understand the petroleum contamination, and this was observed in the lower estuarine regions, while the upper estuarine regions had moderate to low UCM. Further, the petroleum biomarkers were also investigated, and we could see that there was presence of hopanes in high concentration in this region. So hopanes are basically again the petroleum markers, and they are quite recalcitrant towards the degradation, and they also serve as the reliable tool for the petroleum contamination. So PCA, which is principal component analysis, was also performed to understand the interrelationship between various geochemical and sedimentological parameters. And we could see here that these parameters were correlated with each other, and these were the terrestrial parameters, and these were the marine parameters which were correlating with each other. So here I conclude that the lower estuarine region had high energy conditions. There were circulations of saline water, then accumulation of marine phytoplanktons and sea grasses, and also the lower part of the estuary was severely impacted by the petroleum contamination, which could be understood using several proxies, for example, ACL, NAR, and CPI. And furtherly, it was supported by high UCM and hopanes, which are the petroleum markers. So they all anthropogenic proxies indicate the high human intervention in the lower zone. So basically, this study will serve as a baseline for interpretation of various natural and contaminated sources in the coastal environments. Thank you.
Thank you, Bulbul. You finished right on time, but I'm afraid we cannot take in questions. But anyone, if you have questions for Bulbul, please type them in the chat box, and we'll directly, and Bulbul, please see to them so that, you please answer them. So be here and make use of the chat box for at least discussing, because we are like sort of time here. So we go to the next presentation of the session, and it is by Subhajit Sinha. Bulbul, please stop presenting so that
Okay.
Subhajit
Thank
can.
you. Thank you.
Thank you. Thank you so much. Yeah, second presentation. Are you there, Subhajit?
Good morning, everyone. I'm here.
Okay.
Presenting.
Please share your presentation. So Subhajit Sinha would be talking about end-member contribution and sediment exchange in the beach dune system, east coast of India, implications to coastal resilience and hazard mitigation. Yes, you can see your screen. Just put it on a slide mode.
Good morning to everyone. Is it full screen now?
No, I'm afraid we are not seeing the full screen.
Go screen and do it.
Now we have lost your screen altogether. Share your entire screen.
Already shared my screen only.
Yeah, please.
Is it visible?
Yes. Yeah, it's nice. Yeah, please go ahead.
Okay, the coastal zone environment experiences tremendous pressure from different activities, both natural and anthropogenic. Natural processes like waves and tides continuously shape the coastal morphology through erosion, accretion, and shoreline shift that continuously change the beach width and character. The spatial influence of tide wave cycle on the beach morphology is influenced by the exchange of sediment amongst near shore, beach, and dune. The exchange of sediments leads to beach mobility, and high frequency of the beach mobility leads to greater morphological variability. So the beaches actually play an essential role in the ecosystem. They participate in water purification, nutrient renewal, coastal defense, recreational activities, etc. In general, the use of beach does not integrate well with the importance of maintaining these sustainable resources. Moreover, fast-growing tourism, coastal development, and global climate change can worsen the degradation impact. So to better understand their socio-economic and engineering impacts, These erosion problems needs to be assessed via physical processes of the coastal zone. Some of the indicators such as shoreline positions, beach morphology, the sediment character, hydrooceanographic conditions, and of course the coastal structures can be used to assess the erosion problems, which is actually being carried out in this study. And of course, the results of this assessment should be considered for the development of the coastal management. The area of study for this I have chosen because this is a part of West Bengal in the Sundarban complex, and it is the tourist spot also, where each and every year people visit, so many people visit these places. The area I have chosen is, you can see over here, it is written Bakhali. Actually, this is, I have just named it, this is a Bakhali region, but this contains 3 small beaches where people visit. Towards the western part, it is Fraserganj. In the middle, it is Bakhali, the place name. And on the eastern side, it is Henry's Island. This beach is arcuate in shape, and the littoral drift in this place is actually northerly directed. However, while reaching towards the land, these the current is being dissipated depending upon the arcuate shape of the beach. And towards the western side, the another study area is Talshari. This is a part of the east coast, and this beach is actually straight as compared to the arcuate beach of Bakhali, and the littoral drift in this direction is from west to east. Now, shoreline change is also one of the most important thing to see whether the land is being, or the beach is being, the beach area is increasing or decreasing. So to understand this, it's a regular method that we have taken up the satellite images and draped all the shoreline that has been changed through the years. And it is interesting to note that the rate of erosion, overall rate of erosion all through these places is less than rate of accretion. That means accretion is actually going on. However, if you look into the inset of the picture, you can see that there are places, depending upon the place, there is an erosion, and as well as there is accretion. Erosion is being actually more than 100 meters, as well as accretion is also nearing 100 meters. So to understand this, the 3-stage process is being adopted for the analysis and interpretation. Sieving was carried out by after taking up samples from the beach. The transects were actually placed perpendicular to the beach in both the places, and then sieving was done, and the statistics were calculated and they are plotted. Here you can see that in the Bakhali region, for the beach region especially, the mean grain size and sorting are nearly similar. That means there is a homogenization of the beach everywhere. And in the dune field, you can see for Henry's Island and Fraserganj, they are very much similar in grain size and sorting. However, the dune of Bakhali region stands distinctly. Contrasting Talsari region, you can see that the dune and the beach had different characters in their sediments with respect to mean grain size and sorting. The next thing is carried out is the end-member modeling analysis. So this is done in order to estimate the possible grain size end members. Particle size distributions were fed into an R package called MMGO. This R package MMGO code was given by Daisy et al. 2012. And we have only used that one, which derives statistically meaningful particle size end members and quantifies relative contribution of the end members in the individual samples. And this is done through eigenspace analysis in combination with scaling procedures and multivariate methods to describe the dataset as a linear combination of the end member loadings, end member scores, and the associated error matrix. So after all the analysis is being done, you can see below here, N member 1, N member 2, N member 3, and N member 4 has been segregated based on the sediment grain size, which is given in phi, and their percentage contribution within the whole population. This is done for the Bakhali region. The same is also being carried out for the Talsari region, and in both the regions, you can see that the number of N members are same. However, the contributions and the mean grain sizes are really different. Now, the objective of the EMMA is actually to finally find out the.
Sir, hello, sir. This is Anil. I'm sorry to interrupt you, sir. You have only 1 minute, sir. Please conclude.
Okay. So this is actually done, and for the process-based environmental dynamic analysis, this is being carried out for both Bakhali and Talsari region. So coming to the conclusions, we can see that the beach dune system of Bakhali shows appreciable homogenization of sediments compared to the Talsari region. Actually, the study elicited the EMMA-based grain size and had its applicability in segregating the robust N members. Most important is the characteristics of the studied sources, as field observation is much more important to study or to specify how many N members you need to be finding out. And the data presented in this model provides an opportunity to predict the coastal changes with the accurate estimates of the grain size populations, and also which one is eroding and what is remaining. And the last thing is that for beach nourishment, this study will serve as a guide for the different types of sediments to replenish the beach, and this will help the policymakers to make or execute the plans on the ground. Thank you.
Thank you, Subhajit, sir. We can have one question, quick question, if anyone want to ask. I think there is no question. Thank you so much, Subhajit, sir. The next talk is by Arka Sarkar and Vimal Singh. The talk title is "Where is my sediment stored?" Arka Parva?
Yes, am I audible? Am I
audible?
audible?
Please. Yes, please go ahead.
Yeah, just a minute. Is the screen visible? Hello, is the screen visible?
Yes. Please start.
So this particular study was sparked off by a flash flood event from 2018 in Pranmati Basin, Uttarakhand. So I was fortunate enough to be in field and witness this event from the start to the end. And I could see how the geomorphology could change within a couple of hours, say 10 or 12 hours. And it was very intriguing to see how a small catchment could generate so much sediments in a very short time. So the questions that popped in my mind were, where was the sediment all along before the event? Tomorrow, say exactly 24 hours from now, if there is another Rishiganga event or a Kedarnath 2.0, how much sediment is available for mobilization and where exactly are they sitting right now? So starting at the very grassroots level, if I take a traverse along a hill slope from the channel to the drainage divide, I dig a pit at the drainage divide, and there exactly everything starts. Rock weathers and disintegrates and hence becomes mobile. This mobile material moves downslope due to some processes, gets stored in certain pockets within the hill slope, and only a small fraction manages to reach the channel. Question is, where exactly are these pockets located which are storing the sediments? So, little thing about the study area. Pranmati catchment is a small 93 kilometer square catchment in the Chamoli district, Uttarakhand. The slope varies between 0 to 79 degrees with a mean and modal slope of 25 degrees. Hill slopes are mostly soil mantled with bare patches, with bare bedrock patches. Land cover units that we've identified are forest, grassland, cropland, and barren lands. So, to target the questions, we have used the tool of connectivity. So connectivity basically talks about the probability of a point to contribute sediments to the final basin yield. Now, this connectivity is basically a combination of two components. The upslope component, that is the upslope contributing area. Larger the area, higher is the sediment influx, higher is the probability of contribution. And the downslope component, that is the downslope flow path. Longer the flow path, higher is the probability of the sediment getting arrested within the hill slope, lower are the chances of contributing to the yield. So if we see that way, connectivity is basically directly proportional to the upslope component and inversely proportional to the downslope component. To calculate the index of connectivity, we have taken the logarithmic of this expression. Now, if we just simply take the area and the flow path, we are basically assuming that the slope is uniform and the surface characteristics are homogeneous, which is definitely not the case. Hence, we weight these area and this flow path with the parameter of slope and a surface characteristic weighting parameter. That's about contributing of sediments. But what about storage? So for storage, what we did was we basically took the same two components, just we changed the relationships between the component. So for storage at a point, it is larger the upslope area, larger is the contribution of sediments, higher are the chances of storage. And larger the downslope flow path, higher are the chances of sediment getting arrested and storage is possible. Hence, storage potential of a point is directly proportional to both the components. So if we see the spatial variability of these two potentials, we see that they're closely related to the land use and land cover within the catchment. We can see that the barren areas have a very high connectivity. Croplands have a very high connectivity. Areas in and around channels have a high connectivity. While there are certain patches we can see in the southern part of the catchment where we see ultra low connectivity. When we verified them in field, we saw that they correspond to landslides. So basically these landslides and slow failures, they are areas of low connectivity. If we see the storage potential, we see a band of high storage area in the northern part. Croplands, interestingly, are acting as storage units. Areas in and around the channel, they have very low storage potential, while these landslides, they have a very high storage potential. If we see the relationship between the storage index and the index of connectivity, we see that for every land cover unit, these two parameters are inversely proportional. So lesser is the connectivity, higher are the chances of sediment getting stored at that point. Now, does that mean that every low connected area within the catchment has a high storage potential? Definitely not. It's basically a balance like everything in nature. So stronger the upslope component, the area becomes well connected. Stronger the downslope component, it becomes poorly connected. While a very finely tuned balance between these two components, an area can become a storage potential storage area. Now, the storage zones that we identified within the catchment are: number one, high-yielding pockets within poorly connected zones, like grassland patches within forests. Now, this grassland has a very high sediment yielding capacity, but the sediment cannot leave this grassland pocket because the forest is impeding the transport. Hence, they become a storage area. Junctions of LULC units of contrasting connectivity. So, as we see the barren area is actually contributing a lot of sediments. But the moment these sediments reach the junction of a forest and the barren area, they get impeded and they get stored in this junction area. So that becomes an important part. Lower parts of hill slopes outside the direct influence of channel. Now, these are the weaker counterparts of the storage zones, but they are basically that fine-tuned balance between an upslope area and a downslope flow path. Talus cones. Now, talus cones are basically, they have a very high storage, sediment supply, but the carrying capacity is not high. Hence, they become transport limited zones and they start storing sediments. Last, croplands. Now, croplands, due to intense anthropogenic interference, they have a very different dynamics of sediment transaction. And right now we are not delving into that, but these entities, they need to be studied at separate systems. Now, the life cycle of storage system. This is very interesting. So once a storage system forms, we can see that there is pedogenic activity on the stored sediments. There is vegetation growth. Now, the moment there is vegetation growth, the vegetation impedes the transport of upslope in sediment in flux. Now, these sediment flux that get stored in the upslope area of this storage system, which eventually becomes an extension of the storage system. Eventually, that extension undergoes pedogenetic activity, and there is again vegetation growth. This positive feedback cycle goes on, and a storage zone grows upslope. Now, this cycle is disrupted by certain resetting events, like a flash flood. A flash flood comes and it empties the entire storage zone. It might leave behind some sediment, might not leave behind some sediment, but this will bring back the entire system to square one, where the system again starts accumulating sediments. In case these storage zones are converted to croplands, the same resetting event occurs, but at a lower threshold, because croplands tend to have a lower resilience compared to the national forests. So this, you can see basically the evolution of an area. In 2017, it was before the flood. 2018, just a couple of hours after the flood. 2019 and 21, how we can see that the area is slowly evolving. So wrapping up, well-connected zones are regularly supplying sediments, hence low potential to store sediments. Storage zones are characterized by high upslope input while low downslope routing, hence they can store sediments. Low connected areas, but not definitely poorly connected areas. Identified potential storage zones, junctions of two land cover units, high sediment tailing pockets, lower parts of hill slopes, and talus cones. Storage zones tend to grow upslope, feeding on a positive feedback system. The next few steps in the study, parameterizing and quantifying sediment storage capacities of these individual storage zones, determining the rates of release of sediments from these storage zones, and determining threshold of resetting. So that's my time. Thank you. I think we have some time for questions.
Thank you so much, Arka Parva. You consumed all your 10 minutes. No time for questions.
Okay,
if anybody has any question, please type on the chat box. We are moving to the next presentation. Please disconnect your presentation. Stop sharing. We are moving to the next presentation. The presentation will be by Chaudhary Mayam Pankaj Sharma. The title is Understanding the Past Debris Flow of Leh Valley, Ladakh and its Susceptibility Assessment. Pankaj, please
Yes, sir, I'm here.
share the screen.
Sir, is it visible?
Yeah, please start.
Our screen is visible. Hello, good morning, everyone. I'm Pankaj Sharma. I did my PhD under Dr. Braj Srivastava at the Warrior Institute of Himalayan Geology, and I've just submitted my PhD thesis. And so this is a part of my PhD, and I'll be talking on the understanding the past debris flows of Leh Valley, Ladakh, and its susceptibility assessment. So what are debris flows and what's happening in Ladakh? So debris flows are one of the most important hydrological process that has been occurring on the surface of the earth. It has been occurring since the evolution of the surface of the earth, and it is a really highly energetic event, and it is considered as one of the most energetic events like floods. And it occurs because of the presence of debris, and when the debris got mixed up with water, it could get transformed into a highly dense, high density flow with a very high speed, and it can cause a lot of destruction to anything that obstruct its path. That includes that may include the human settlements and infrastructural activities. That can be, it can be highly dangerous. So such kind of events occurs mostly in mountainous areas because of the presence of debris and because of the high rugged nature of the terrain. So globally, in the last 50 years, more than 70,000 people have been died because of debris flow disasters. And in Himalaya, in Ladakh, which is in the Western Himalaya, is no exception. So Ladakh it also suffers from debris flow disasters. And in 2010 flood in Ladakh, debris flows have, the flood has caused a series of debris flow in many valleys of Leh, and that has killed more than 60,000 people. I mean, around 6,000 people have been killed. 6,000 people have been killed there. So it is highly dangerous, and so this needs to be assessed very well. So as a geologist, we need to understand what has been, how the debris flows, what is the role of debris flows in the landscape evolution, and how do we assess the susceptibility of this hazards. So in order to understand the past flows, we analyze certain debris flows that occurred in the past, and we map some of the flows, and we try to arrive at the chronology of the flows. And for assessing the susceptibility, we use we explore three techniques: the index of connectivity, the flow R, and web of evidence method. So this is how debris flows looks like in Ladakh. The top left corner is an older debris flow that has been preserved in a stream at Sabu village. At the bottom left corner is another flow that has been found in Nang Fen in Leh Valley. This is at the upper part of the upstream part of the fan, and this is how it looks like in the upper part, because the upstream portion is associated with high energetic flows, whereas the right side this is in Tikse fan. This is same kind of a flow, but the energy get reduced. So most of the glass and boulders get deposited elsewhere, and only the slurry gets downstream there. So we have explored many sections in this, three of them. One at Sakti, one at Phayang, and one at Nang. And here what we can see is this. We are seeing a lot of series of debris flow episodes, and these episodes are demarcated by well-defined or not so planar, but it's kind of not planar, well-defined. Sorry. I'm sorry. So these flows are demarcations. This flows source a series of episodes of flows, and it is demarcated by difference in density, difference in energy, because we have different class sizes, different matrix content, and we have also done some chronological understanding using luminescence edges. And most of these flows, the ages of these flows can range from 10,000 years before present to as young as 2,000 years, and we can see a series of flows here. So this is how debris flows have been known to be an important mechanism of landscape evolution, especially in Leh Valley. In order to assess the susceptibility, we use three independent techniques. One of them is the index of connectivity. This concept has been explained very well in the last presentation, and so here we use two kinds of data, which is upslope component and a downslope component, and these are all function of a slope area and a wagging factor, which is the roughness index that we have used in this context. So this is the index of connectivity map of the Leh Valley, and what we can see here is the Phayang, Sakti, and Kharo. These areas are highly connected. Entire valley is highly connected, whereas other valleys such as Leh, Sogamsar, and Stakmo, these areas have lesser connectivity. Even though the upstream portions are highly connected, the downstreams are have a low connectivity. In the second stage, we have used flow R. We have applied flow R algorithm. So flow R algorithm is developed in the University of Lausanne in 2013, and it is used to assess the debris flow disasters in Alps, and we are testing this algorithm in Himalaya, and this technique provides the potential source area and the propagation extent. So the source area here any gullies which has higher than 15 degree slope and with having a upslope area of more than 100 meters square is considered as a potential source area, and the propagation is being computed based on this, and this is the resulting model that has been computed using FlowR. So the FlowR model and the index of connectivity model seems to be quite, agreeing when they have similar kind of results. Most of the zones demarcated by high convergence of debris by FlowR are also highly connected. So these two models are counter-supportive, and we think this model can be used to understand the flows where it can originate, debris flows it can originate. So this can be used here. However, as we know, what we know is that other areas in the downstream portion, such as this lay area in Toglamsar, all these areas are heavily affected and in the last decade by debris flow. So what we think is that such kinds of flows occurring in the last decade is a process that has been resulted because of convergence of all the individual streams, and it gets modified because of the convergence of drainage network on the flatter part of the fan. But such kinds of flows are not being able to assess by these two methods, index of connectivity and FlowR. So we attempted another technique called as the good old weight of evidence method. So this is a Bayesian data analysis method. Here we use two kinds of data. One is the evidence of debris flow, and another one is the factors. So debris flow evidence that we have mapped from the field works, and then we have used these areas as evidence, and factors are some of the topographic indices that we have generated from the DEM. These are the topographic wetness index, stream power index, stream transport capacity index, slope, plane curvature, stream density, and aspect. So we have these are the factor maps of the method that we have used, and this is how the pixels are being classified. Those pixels where factors and debris flows, evidence and factors coincide is classified as NPX1, where there is only evidence but no factor is there. It is classified as NPX2, where there's only factors but no evidence, it is classified as NPX3, and when both of these are not present, it is classified as NPX4. So based on these four variables, we have fed these variables into the equation, and we have computed the weight of each model, and we have compiled this model into one singular susceptibility map. This is a susceptibility map that we have built using this model, and we've also tested the validity of this model using some other flows that we have kept to test for the validation, and we found that about 80% of the validation has been explained by the model, and we think this is quite good. So this model,
Pankaj,
model.
Your time is getting up, so just wrap it in 1 minute.
Yes, ma'am. So this is the weight of evidence model accounts for all those flows that will originate, that will happen in the downstream areas when all the streams get converted into other flows as hyperconnected flows. So the take-home message is debris flows in Ladakh will be occurring regardless of human intervention, and the weight of evidence and FlowR model seems to be counter-supportive, and they can explain the flows that will originate in the upstream portion, whereas those flows that are found in the downstream portion cannot be, explained. This is a limitation of these two methods. This is being compensated by the weight of evidence model, and these models can be used for other preliminary information for town planning activities, and further development of the model is being suggested here. Yeah, that's it. Thank you very much.
Thank you, Pankaj. It was a very interesting lecture on the debris flows, and yeah, in the future you can also see whether what is initiating these debris flows. Is it the tectonics or the climate? Like in the keynote, Professor Clift, he was talking about that. So yeah, we don't have time for questions, but if anybody has questions, please type them in the chat box. Pankaj, you please see to them. So we go to the next presentation. You can stop sharing your screen. And I invite Kuldeep Datta to present his paper. And Kuldeep, please share your screen.
Yes, ma'am.
So Kuldeep Datta, Vijay Kumar Mishra, and Nishchal Vanchari are the authors of this paper. And we will be talking to us in from two things. Yeah, I think there's a disturbance from your side. Just see that it's okay. So Kuldeep, you share your screen and then unmute yourself and talk about characterization of rainfall spells initiating landslides in parts of East Sikkim, Eastern Himalaya, comparative analysis of IMD and NASA daily rainfall data. So over to you, Kuldeep. Kuldeep, you're mute and we are not even seeing your screen share. Hello, Kuldeep. If you can hear us, please unmute yourself. Yeah, good. We see your screen now. Please select the full screen mode or share your entire screen, and please start your presentation, otherwise we lose time.
Hello, ma'am. Am I audible now?
Yeah, you're audible. Yeah. Have you logged in two places? Because I see two places. So maybe one, if you could.
Yes, ma'am.
Just,
I already logged out from.
So this lag of audio won't come like this. Yeah.
Yes, ma'am.
And please hurry up so that yeah.
Yes, ma'am. Is it okay now, ma'am?
Yes. Please go ahead.
Thank you, ma'am. Good morning, everyone. Today I am going to present characterization of rainfall spells initiating landslides in parts of East Sikkim in Himalaya, India. So, as we all know, that landslides have always been a major problem in mountainous region along highways and main cities and towns. Major settlements, landslides have always been a major problem. And we all again know that different intrinsic and extrinsic factors combine together to initiate and activate landslide. So among the different extrinsic factors like rainfall and different seismic activities, tectonic activities, rainfall is the most frequent and main extrinsic factor that initiate landslide. And in this study, my study area is one district of Sikkim, that is Eastern District of Sikkim. And my objectives of this study is to understand disparities in rainfall spells of East Sikkim and to delineate type of rainfall spells that initiate landslides in East Sikkim. So in my methodology, I have used two different daily rainfall data, that is IMD rainfall data and NASA power rainfall data. And again, to prepare my landslide inventory, I have accessed GSR.
Hello, Kuldeep, are you there?
Hello, Kuldeep, is there a problem? Kuldeep, we really cannot hear you because
Yes, that calls.
we are stuck. Is it from our side?
No.
If someone has his phone number, please call him. He may not know that he's not audible anymore.
Oh, he's left. Oh, I think there is some problem. Maybe we can take that paper later because we don't want to lose time. So, Rajiv, I think this was the last presentation of the Earth surface process session. And it is over to you for the oceans in Quaternary session. So moderators are Dr. Rajiv Saraswat from NIO and Dr. from BSIP. So I hand it over to you to conduct this session.
Thank you, Dr. Benita. Good morning, everyone. We'll move on with the next oral session that includes several papers from the oceans in Quaternary. So that's a theme which is basically includes contributions in the oceanic realm. With me, this session is moderated by Dr. Pavan Govil from the Birbal Sahni Institute of Paleobotany. So the
Good morning to all. You can start the
presentation is by Divya Verma and Pavan Govil. I believe Divya is going to present it. The title of the talk is Paleoproductivity Variation based on Planktic Foraminifera record from Agulhas Plateau IODP site U1475. Divya, are you around?
Yes, sir. Yes, sir.
Yeah, please share the screen and start presenting. Pavan, please keep a track of the time and inform the speaker after 8 minutes.
Yeah, sure. Yes.
So my slides are visible?
Yes, please go ahead.
Okay,
Go ahead.
thanks. Good morning, everyone. Myself, Divya Verma, and I'm working with Dr. Pavan Govil as a Junior Research Fellow in Birbal Sahni Institute of Paleosciences. I'm here to present a part of my PhD work on paleoproductivity variation based on planktonic foraminifera record from Agulhas Plateau, IODP site U1475. So the Agulhas Plateau is present in the Indian Atlantic Ocean gateway, from where the water mass exchange takes place between Indian and Atlantic Ocean. This exchange of water between these two oceans is a key part of global thermohaline circulation. Indian Atlantic Ocean gateway consists of pronounced frontal system, and these fronts are the essential component of hydrography of this gateway. So the migration of these fronts, especially subtropical front, has been proposed to impact the upper ocean hydrodynamics and drive the local nutrient availability and regional export production. Coming to the study area, this figure is representing the location of core U1475, which is collected from Agulhas Plateau at 41 degrees south latitude and 25 degrees east longitude. So these arrows are representing the surface current of the study area. This south equatorial current splits into northern and southern branch when it reaches to Madagascar, and forming the Southeast Madagascar current and Northeast Madagascar current. This southern extension of Southeast Madagascar current converged with southward flowing Mozambique channel eddies to form the Agulhas current. This Agulhas current, once it reaches the southern tip of Africa, it reflected eastward back in the Indian Ocean. Some Agulhas water leaks into the Atlantic Ocean as ring shading, which is known as Agulhas leakage, and it is suggested to have an impact on Atlantic meridional overturning circulation in Atlantic Ocean. So why I have chose this core site, because through literature survey, I found that most of the studies in Indian Atlantic Ocean gateway has been done close to the southern tip of South Africa, and comparatively less attention is given to areas under the direct influence of frontal zone. So I chose this core site because it is closer to the present day position of the subtropical front. So, despite of the numerous studies on the southern Indian Ocean, which is linked to the subtropical front migration and to variation in productivity, but there the understanding remains limited regarding how these biotic communities have responded to change in water column nutrient and productivity with varying subtropical front position over glacial and interglacial cycle. So here we focus on planktonic foraminifera community to study the past variation in the productivity of the Aglhas Plateau from the southwestern Indian Ocean up to the last 120 kilo year, and also to understand the migration of subtropical front during the last glacial interglacial cycle. So yeah, these are my objectives. So for this study, samples were obtained from the International Ocean Discovery Program Expedition 361 from the Kochi Core Center of Kochi University, Japan, and the age model for the Aguilas Plateau composite is constructed by Star et al. From two sediment core, which is one MD022588 and IODP site U1475, which has been used in this study. And these are the foraminiferal extraction process. First, we dried the wet sediment sample in an oven at 60 degrees Celsius, and then we soaked these samples in distilled water overnight. Then we treated the samples with 10 ml of 10% of sodium hexametaphosphate and 5 ml of 10% of hydrogen peroxide solution. Then after we wet sieve the sediments by using 63 micron sieve. So, then the wet sieve remnant dried at 50 to 60 degrees Celsius, and it further dry sieved using 250 and 150 micron sieve. Then after the foraminiferal picking and abundance count was done on 150 micron coarse fraction.
Divya, you have 3 minutes left.
Okay, sir. So coming to the result in this study, we have used a planktic foraminifera species, Globigerina bulloides, as a tracer for change in surface productivity because according to Shibel et al. In 1997, bulloides are abundant during periods of high phytoplankton productivity. So as a result, the temporal variation in the relative abundance of bulloids have been proposed as an effective tracer of previous changes in surface productivity caused by wind-driven upwelling. So in this figure, the relative abundance of bulloids has slightly increased in the middle of MIS5 and decreased up to MIS4. It further increased during the middle of MIS3 and also in MIS2 and decreased towards the MIS2 to 1 transition and also in MIS1. So this high increase in abundance during these periods suggests high productivity and low relative abundance suggests the low productivity. This fraction greater than 63 micron percentage is quite well matched with the records of bulloids, which is showing the increase throughout the MIS5 and decrease in MIS4. It also showing the increased rate in MIS3 and MIS2 and sharply decrease in MIS2 to 1 transition and also in MIS1, which is also showing by the G bulloids records. So this high productivity during these periods might be attributed to equatorward shift of subtropical front, whereas poor productivity during MIS5 and 1 could be attributed to a poleward shift of the STF. So as we can see from the tropical and subtropical records, it is showing a decreasing trend in MIS4 as well as in MIS2, which might be suggest the lower influence of warm and subtropical, warm and saline Aglhas return current because of the shifting of subtropical front in northward position. And also it is showing an increasing trend during the MIS5, MIS3 as well as in MIS1, which might suggest the greater influence of these warm and saline Aglhas return current and because of the poleward shift of the subtropical front. So here are my conclusions, which that the increase in relative abundance of bulloids during MIS2 and MIS5 suggest high productivity during these periods, and these high productivity may be attributed to equatorward movement of the STF, whereas the low productivity during these periods could be attributed to a poleward shift of the STF. So this increase in relative abundance of tropical and subtropical fauna during early and latter part of the MIS 5, 3, and 1 may be due to the influence of warm and saline Aglhas return current. So that's all from my side. Thank you.
Thank you, Divya, to finish it within the time. Questions are welcome now. Rajiv, sir.
Yeah, Divya, it's a nice presentation and a nice work from a very important area. Really good that we are now looking at the Southern Ocean course also in detail. I mean, this pattern, did you realize that this pattern is almost opposite to what we see in the Arabian Sea? The productivity seems to be quite low during the MIS2 in the usual Arabian Sea coast. So any idea what is it, why is it so? You got what I'm asking?
Yes, sir. So because of the subtropical front shifting which takes place during the glacial periods, which is a very high productive zone.
Mm-hmm.
So so because of this, their productivity is high, I guess.
Okay. Mm-hmm. It's good to compare that with the other records from, say, either Eastern Arabian, the Arabian Sea or some parts of the Bay of Bengal. It will be good if you compare that with some of the other records.
Yes, sir. Yes, sir. I will do so.
Yes, please, Rajiv.
Yeah, Narendra wants to ask a question. Please, quick question, Narendra. Go ahead.
Yeah, yes.
Ma'am, just you said that the subtropical fronts are shifting. So, can you focus on the mechanism? Which mechanism is applied for this shift?
It may be due to strengthening of westerlies wind in the Southern Ocean.
No. Westerly, how westerly can shift the front? The westerly is the result of the shifting of the front. Maybe it's just regular winds. So, what mechanism shifts the whole package? Can you focus on it?
So it may be due to the extension of glacial ice sheet.
Okay, then.
Yes.
Which ice sheet?
You can please go and discuss afterwards. So let's move on to the other presentation.
Other presentation. Yes.
Okay. Thanks a lot, Narendra. Thank you.
Thank you, sir. Thank you.
So the next presentation is by Harshit Singh, Ravi Tripathi, Kuhu Madhav, and Arundev Singh. I believe it's a student working with Professor Singh. His talk is Rapid Oceanographic and Climate Variability in the Northeast Atlantic Ocean across the terminations 1 and 2 for hemiferal evidence from the IODP site U1385. So we are continuing in the Atlantic. Harshit, please go ahead.
Okay, sir. Thank you, sir. So is my screen?
8 minutes for the talk and 2 minutes for the discussion. Please start.
Okay, sir. Thank you, sir. So is my screen visible?
Yes.
Yes, please go ahead.
Okay, thank you. Good morning, everyone. I am Harshit, a research student from Department of Geology, Banaras, Hindu University. I'm here to present a topic and rapid oceanographic and climate variability in the Northeast Atlantic Ocean across the terminations 1 and 2 for aminiferal evidences from IODP site U1385. This work is part of IODP Expedition 339 and is supervised by Professor A.D. Singh. We chose this site because Iberian margin is unique in having association to both the poles as well as the tropics. Also, the millennial scale variability recorded from this site can be correlated with other marine sequences, ice cores, as well as European terrestrial records due to its various age models, which makes the correlation very meaningful. The site is under the influence of westerlies, which are a very important atmospheric circulation in the mid latitudes, which has a crucial role to play in the northern hemisphere climate change, as well as has teleconnections with the Asian monsoon. Also, this site is under in close proximity of European ice sheets. Thus, study of this site could shed more insights on the role of European ice sheets during Heinrich stadiums. Our time period includes the terminations, which are glacial interglacial transitions of highest amplitude climatic fluctuation for the last few million years. These involve large-scale freshwater perturbations resulting in fluctuations in AMOC. Every termination is unique in terms of the external and internal forcings. Also, the unique sequence of events that interrupt these terminations subsequently pace the upcoming interglacial. Having said that, termination 1 has been very well studied, but termination 2 is still rare, probably due to chronological uncertainties. However, whatever handful of studies do exist, they have shown that Heinrich stadiums do interrupt these terminations and probably play a very crucial role during the deglacial process. These studies have also shown that MIS 5E could be a very good analog for Holocene and its future prediction. Because it becomes crucial to compare these terminations to understand the common processes at play and to delineate the ones that are unique. With having that in mind, we studied the last two terminations in finer details from IDP site U1385 from North Atlantic Ocean using planktic foraminifers. Our site U1385 was drilled in southwest Iberian margin and is also known as Shackleton site in the honor of Nick Shackleton's seminal work. The surface hydrography of this site is modulated by North Atlantic current and its branches, Portugal current and Azores current. Also, the frontal migration such as polar and subpolar front migrating south and subtropical front migrating north modulate the surface hydrography of this region. The surface water mass is North Atlantic surface water. Beneath it lies the Eastern North Atlantic central water of subtropical and subpolar origin, with subpolar one being nutrient enriched. The surface hydrography of this region is strongly modulated by a strong seasonal pattern. During the summer, this high strengthens and shifts north, thereby increasing the influence of trade winds, which result into upwelling of subsurface waters. At the same time, Portugal current intensifies, which result into dragging of Eastern North Atlantic central water of subpolar origin, which results into high productivity. However, during the winter, the circulation reverses and westerlies become the dominant wind direction, which intensify Iberian poleward current, which drags with itself the Eastern North Atlantic central water of subtropical origin, which results into a productivity decline. For this study, we studied the last 20 kiloyears and 110 to 140 kiloyears. The age model of the site is based on correlation of log Ca by Ti records with adjacent sites having well-developed age model, which gives us a resolution of 150 years and a centennial resolution for Holocene. We reconstructed our SST data with artificial neural networking technique using the Margo North Atlantic database, following the methods of Kucera et al. 2005. We also reconstructed various planktic foraminiferal proxies such as a polar front using N. pachyderma, Arctic front using T. quinqueloba, Azores front using tropical subtropical species, Portugal current using Incomta inflata, and surface productivity using Buloides and Glutinata. These proxies are based on recent surface trap studies as well as previous studies from this region. We further integrated our results with previous results of North Atlantic.
You have 3 minutes, Anshul. You have 3 minutes to wrap up.
Sir. In total, we documented 31 species. Out of those, 6 ones are shown here. Our SST reconstructions are in agreement with the present value. So when we compared both the terminations, our sequence were very different for both the terminations. Termination 1 was interrupted by Heinrich stadial 1, B by A and YD, whereas termination 2 was interrupted by a sole stadial Heinrich stadial 11, even though the external and internal forcings were very much similar. Both the terminations were similar in terms of SST gradient as well as durations. Also, when we compared both the interglacials, we found a late cooling trend during the late stages of interglaciation, which could probably be due to the cooling of decrease of insulation values. Also, we found brief cold events in the progression of both the interglacials, which upon correlation with higher latitude delta C13 records showed that these cold events were occurring coeval with reductions in NADW. This suggests they can have a NADW or AMOC origin. Also, polar front migrated further north during Heinrich Stadial 1 as compared to Heinrich Stadial 11. Also, we found a brief warm event in the progression of Heinrich Stadial 1, which is of amplitude 5 degrees centigrade. We also found two cooling phases in the Heinrich Stadial 1, 1.1 and 1.2. Similarly, during Heinrich Stadial 11, we found three cooling stages, 11.1, 11.2 and 11.3, interrupted by two warm phases, 2.5 and 5 degrees centigrade, which gives both the stadial a characteristic W shape. Upon correlation of our results with other records of North Atlantic, we found that this Heinrich stadial structure is common for all of them, which suggests that this W structure was characteristic of this mid-latitude. And from here, the Heinrich stadials were not a simple fold anomaly, but also were interrupted by a brief warm event, which gives us to the mechanism, how it happened. Odell et al. In their study from IRD Basin suggests that both these ice sheets, both these cold events have different ice sheet origin. Heinrich Stadial 1.1 originated due to melting of European ice sheets, and Heinrich Stadial 1.2 originated due to melting of Laurentide ice sheets. So this brings us to the mechanism, which is melting of European ice sheets led to the decrease of AMOC, which resulted into a reorganization of atmospheric circulation, which caused summertime warming, which is also evident from our seasonal SST contrast during this part. In this summertime warming in conjunction with intermediate depth warming led to the collapse of marine-based ice streams, that is Laurentide ice sheets, which led into the major role of Laurentide ice sheets during Heinrich Stadial 1.2. We also reconstructed Azores front or Portugal current, which were very diminished during terminations, but regained their strength during both the interglacial. Though there were some short peaks, Portugal current while was decreasing during the middle and early part, but regained its strength during the late part. Productivity fluctuation for both the interglacials saw a very similar trend. It was declining in the start, but then in the middle it recovered a maximum and then started declining later. Also during Heinrich stadials, we found a productivity decline, though there were some peaks that cannot be ignored, which could be probably due to vertical mixing due to increased windiness recorded from dust and pollen records, which brings us to our conclusion that both the terminations were very similar in terms of ST gradient and erosion, even though the sequence of events were different. Heinrich stadial, that is terminal Heinrich stadial from these latitudes weren't cold anomaly, but also contained a warm event, which suggests a crucial role of European ice sheets and Fennoscandian ice sheets in shaping these stadials by collapse of or shutdown of or slowdown of AMOC. Holocene and MIS 5e were interrupted by multiple brief cold events due to AMOC origin. Also, a cooling trend during the late stages is also very much evident. A similar progression of both the interglacials, MIS 5e and Holocene, was evident in terms of SST and productivity. However, frontal migrations differed. Thank you.
Thank you, Harshit. I'm sorry, we don't have much time left. So if there is any question, please put it in chat, and Harshit, please respond to the questions people are writing in the chat.
Okay, sir.
Very good work. Please keep it up. Thank you.
Thank you, sir.
Very good work, Harshit.
Thank you, sir.
So we move on to the next talk, which is by Hidayatullah Khan from BSIP, and the title of the talk is Southwest Monsoon Response to Surface Hydrographic Variations in Western Arabian Sea through the last 172 kilometers. Hidayat, are you around? Please unmute yourself. Go to the PowerPoint. Go to your PowerPoint presentation. Yeah, now slideshow mode, and then that's it. Yes. Yeah, please go ahead. Hidayat, I think you have to unmute yourself. We can't hear anything.
ये क्यों बार-बार ऐसा कर रहा है?
Presentation is fine. Only thing we are unable to hear you.
Otherwise, we can move ahead, Rajiv bhai, and we'll ask him to come to committee room and present from here. The next presentation we'll take from him.
Fine.
So we can move to the next one.
Yeah, please. Okay, so the next talk, I hope, Nisha, are you around? Nisha. Kumari, Nisha, are you around? Okay, fine. So the next talk is by Nisha, Sushant and Barnita, and she'll be talking about changes in deep water circulation in the equatorial Indian Ocean during the last 25 kilo years, evidence from carbon and oxygen isotope of benthic foraminifera. Nisha, please go ahead. Can someone from the committee room help her? She is unable to unmute herself.
Nisha.
Is it possible to unmute her from the organizers?
We are trying, but it is not happening. You can unmute someone else. She has to do it on her own.
We are unable to unmute you from here.
Nisha, you have to unmute yourself. Otherwise, you log out and log in again, please.
Okay, then you can go to the next presentation.
Nisha, please log out and log in. Then meanwhile, we'll move on to the next one. Okay, so the next talk is by Latika and Rahman and other authors. And the talk is about deep water circulation in the Arabian Sea during the last glacial cycle. Latika, if you are around, please go ahead. Latika.
My goodness.
Latika, are you around? Please say yes or no. No, I don't see her.
Hidayatullah is here. Maybe you can take, we can present.
We'll start by Hidayatullah. He is here.
Fine. Please go ahead. Go ahead.
दस जगह का
Hello. Hello, sir. This is Nisha here.
Pawan, if there is any delay from that side, then we can ask Nisha. She is now online.
No, Hidayatullah is here. Rajiv, yeah.
Okay, fine. Nisha, just wait after Hidayatullah.
Okay, thank you, sir.
Yeah, good morning to everyone. Myself Hidayatullah, and I am working as a SRF under the supervision of Dr. Pawan Govil at Birbal Sahni Institute of Paleosciences. The topic of my presentation is Southwest Monsoon Response to Surface Hydrographic Variation in Western Arabian Sea through the last 172 kiloyear. Now we will start in introduction. The Arabian Sea region is characterized by a seasonal reversal of dominant wind direction. The Western Indian Ocean, particularly the Western Arabian Sea and Western Arabian Sea, the surface and thermohaline hydrography strongly influence the regional as well as the global climate system. Therefore, if there is any change in the upper oceanic water column, surface or thermocline, they provide essential information for understanding the past climate dynamic variations in the tropical wind intensity and in oceanic heat transport. Hence, the annual temperature contrast in the both area, particularly Western and Northern Arabian Sea, is similar but opposite between season, that is summer and winter monsoon. The map shows the study area. The star mark shows the present core location, and the black dot circle indicated the study covered by previous authors, and the detail of present study core location is the station ID is VM3504PC, which is located at 50 degree 21 minute north and 50 degree 02 minute east, with the core length of 810 meter 10 centimeter, and the water depth is 2590 meters. These are the annual distribution of sea surface temperature, salinity, and oxygen in the Western Arabian Sea. The first figure shows temperature and followed by the salinity and oxygen concentration. The Western Arabian Sea is mainly influenced by the upwelling which brings cold and nutrient-rich water from the deeper part of the ocean to the surface ocean. And here you can see the Northern and Western Arabian Sea have approximately similar sea surface temperature and also same sea surface salinity. But when we are talking about oxygen concentration, the low oxygen concentration is occur in the Western Arabian Sea because of the oxygen consumption by the marine organisms. Here you can see the seasonal distribution of sea surface temperature in Western and Northern Arabian Sea. During southwest monsoon, the Northern Arabian Sea water are stratified, while the Western Arabian Sea water in Western Arabian Sea, the upwelling has been taken place. That's why here we got the low sea surface temperature, and the phenomena is totally reversed during the northeast monsoon. The Western Arabian Sea the Western Arabian Sea water column are stratified. So here the annual and seasonal distribution of sea surface temperature, that means if we are talking about seasonal sea surface temperature, the northern and during southwest monsoon, the Northern and Arabian Sea is totally reverse. But when we talk about the annual sea surface temperature, so they are showing approximately same temperature. The recorded sea surface temperature in the Western Arabian Sea ranges from 22 to 26 degrees Celsius during the southwest monsoon and northeast monsoon respectively. In contrast, in the Northern Arabian Sea, the sea surface temperature ranges from the 28 to 22 degrees Celsius during the southwest monsoon and northeast monsoon respectively. Here I am showing the present study core VM3504PC. These are the result of my core. So the chronology is established with the help of 5 radiocarbon dates and the tie points. The 1 radiocarbon dates were obtained from the direct AMS, and the 4 radiocarbon date were obtained from the IUAC New Delhi. And beyond the radiocarbon 14 dating, we have tuned the delta 18 oxygen of G rubber with LR04, which is commonly known as the which is given by the Lesky and Romeo. These are the sedimentation rate of my core. It varies from the 3.4 to 15.2 centimeter per kilogram with an average sedimentation rate is 4 centimeter per kilogram. Here, these are the result of our study locations. The delta 18 of G rubber, the more fluctuation is mainly occurred during the MIS 5 and MIS 1, and very low fluctuation is obtained during the MIS 6 and MIS 2, and a stable during MIS 3. As we all know that G rubber is mainly found in the oligotrophic condition, which mainly prefer to live in the warm and low saline water, while the G bulwide is basically found in the eutrophic condition, that is where the more nutrient is available, and the ratio of G bulwide and G rubber ratio is most valid proxy for the past change in the intensity of the upwelling. So here you can see if the higher abundance of G bulwide during MIS-E, MIS-5E, MIS-1 and mid MIS-4 and MIS-1. They suggest that the Western Arabian Sea is mainly influenced by the upwelling due to the strong southwest monsoon. And in contrast, you can also see the higher relative abundance of G rubber and lower relative abundance of G bulwide. That means it clearly indicates that the water are more stratified during MIS6. And now we are, you can see in mid MIS4. During mid MIS4, the higher abundance of G bulwide and lower abundance of G rubber, that reveal that the productivity is also high in mid MIS4. This faunal proxy is also supported by the geochemical proxies such as delta 18 of G rubber. And these are the comparative study of my locations. These are this synchronous with each other. Here delta 18 of G rubber of our core, and we compare of our result from the other Indian Ocean records. So they show similarities with each other. And now here are the conclusion of my study. The maximum productivity occurred during the interglacial period MIS 531 due to intensification of southwest monsoon, while the negligible or low productivity occurred during the MIS 6. The mid MIS 4 65 to 6 to 60.3, they show warming period based on the planktic foraminifera and stable oxygen isotope. The present studies show the less negative excursion of in comparison of Bay of Bengal and equatorial Indian Ocean due to the freshwater influx from the Indian continent and transport of warm water from the Western Pacific via Indonesian through flow to Indian Ocean and overhead precipitation. Thank you for your kind attention. This is my.
Thanks a lot, Hidayat. Thanks for the presentation, and we'll move on to the next talk because of the time constraints now. If anyone has the questions, please put it in chat box, and we request Hidayat to respond to the questions put up in the chat box. So the next presentation is by Kumari Nisha, and she'll be talking about changes in deep water circulation in the equatorial Indian Ocean during the last 25 kilo years. Evidence from carbon and oxygen isotope of benthic foraminifera. Nisha, please.
Thank you, sir. Is my screen visible?
Yes, please go ahead.
Yes. Good morning, everyone. Myself, Kumari Nisha. I'm pursuing my PhD from CSI Goa under the supervision of Dr. Shashank Naik. Today, I will be presenting on changes in deep water circulation in the equatorial Indian Ocean during the last 25 kilo year, evidence from carbon and oxygen isotope of benthic foraminifera. Most of us here know thermohaline circulation, how it plays a very important role in modulating and regulating the Earth's climate. There has been changes in deep water formation in the past which has affected the deep water circulation in the Indian Ocean. Information about the past changes in the circulation can be very useful in understanding the future changes in Indian Ocean deep water circulation. One of the ways to infer the changes in past circulation can be by reconstruction of stable carbon and oxygen isotope using shells of benthic foraminifera. The distribution of delta 13C depends upon photosynthesis and remineralization of organic matter. During photosynthesis, there is a preferential uptake of 12C by the phytoplankton, making the surface water enriched in delta 13C. When this organic matter sink to the bottom and are decomposed, they release 12C into the water, making the deep water depleted in delta 13C. Here are some of the water masses and their delta 13C value. The delta 18O of benthic foraminifera reflects the delta 18O of the water in which it calcified and the temperature of calcification. In this study, I will be using epibenthic Cbicidus bulostrophy since it dwells near the sediment water interface and records the delta 18O and delta 13C of the ambient water. To carry out this research work, a gravity core SSD 044 GC01 was retrieved from a depth of 3,160 meters from the northern Indian Ocean during the RV Sindhu Sadhana 44 cruise in 2017. The chronology of the core is based on 13 AMS radiocarbon dates of the plantic foraminifera, which was calibrated to calendar age using Calib 8.2 software. At present, the core is ventilated by upper circumpolar deep water, which is a mixture of North Atlantic deep water and Antarctic bottom water. NEDW is characterized by enrichment in delta 13C. It is a better ventilated water and is poor in CO2 and nutrient content. Whereas the Antarctic bottom water is enriched in delta 13C, it is poorly ventilated and enriched in CO2 and nutrient content. This is a procedure that I followed for sediment processing. For stable carbon and oxygen analysis, epibenthic Cbicidus bulostrophy was identified and picked using stereozoom microscope. Around 3 to 4 for intact foraminiferal tests were picked from a size range of greater than 250 micrometer. The analysis was done using delta plus XP mass spectrometer. The precision of delta 13C is plus minus 0.06 per mil, and for delta 18O it is 0.08 per mil. Coming to the result, the delta 13C values range from minus 0.6 per mil to 0.4 per mil. If we see the graph from LGM to the early deglaciation, we can see a decreasing trend in delta 13C values, which indicate dominance of nutrient-rich water mass at that time. From the boiling era, the delta 13C values started to increase, and high values of delta 13C during Holocene indicates enrichment. Enriched delta 13C water mass was present at that time. The delta 18O of benthic foraminifera range from 0.45 per mil to 0.25 per mil. The maximum delta 18O value was recorded during the LGM, and the depleted delta 18O value was recorded during the Holocene. The delta 18 shift from the LGM to Holocene exceeds the ice volume effect by 0.4 per mil, which indicates that they indicate cooling of deep water by 2 degrees Celsius during the LGM as compared to the Holocene. Coming to the discussion, here I have compiled delta 13C values along with the calcium carbonate course fraction and ventilation age record from the same core. The calcium carbonate is calculated from the total inorganic carbon analysis, which was carried out using coulometer instrument. Course fraction is taken from Yadav et al. 2020, and the ventilation age is calculated as the difference between the radiocarbon age of paired benthic and plantic foraminifera. If we see during the LGM, the low delta 13C indicates nutrient-rich water was present at that time. Low value of calcium carbonate and coarse fraction indicate inflow of CO2-rich water, which resulted in dissolution of foraminiferous shells. Coming to the ventilation age, during the LGM, we can see that the ventilation age was very high at that time. So therefore, from this record, we can say that during the LGM, there was less export of better ventilated NEDW, and there was more inflow of nutrient-rich and CO2-rich southern source AABW at the time. This can be because of weakening of NEDW formation during the LGM. Coming to the HS1, we can see the values of delta 13C calcium carbonate and the coarse fraction further decreased, and the ventilation age reached up to 3000 years. This period was associated with almost complete shutdown of Atlantic meridional overturning circulation, which led to shoaling of NEDW. So we can say that during the Henry Stadial, the dominant water in the northern Indian Ocean was nutrient-rich, poorly ventilated southern source Antarctic bottom water. From 14 kilo onwards, we can see there was a positive increasing trend in the delta 13C calcium carbon coarse fraction value, and the ventilation age also decreased. This indicate that there was resumption of Atlantic meridional overturning circulation, which resulted in extensive export of North Atlantic deep water into the northern Indian Ocean. Enriched value of delta 13C calcium carbonate and coarse fraction during
Nisha, please wrap it up.
Yeah, okay. And low value of ventilation age during the Holocene indicate progressive influx of better ventilated 13C rich NEDW. These are my conclusion. The stable carbon and oxygen results indicate that the deep water circulation at the core site during the LGM was very different as compared to the modern ocean. The depleted delta 13C indicate reduced flow of better ventilated NEDW and enhanced inflow of nutrient-rich southern source AABW into the northern Indian Ocean. During the HS1, due to collapse of NEDW formation in the North Atlantic, deep water masses in the northern Indian Ocean was dominantly delta 13C poor and CO2-rich AABW. At the onset of boiling Eroded, there was an abrupt increase in delta 13C rich water flow in the northern Indian Ocean, indicating resumption of NEDW formation. And this delta 13C during the Holocene suggests penetration of northern source better ventilated delta 13C rich NEDW in the northern Indian Ocean. Acknowledgement. Thank you.
We can take one quick question if anyone has.
Hi, Nisha. I have one question out of curiosity. So you have interpreted the delta 13C of Bentic Forum as a deep water mass proxy. How did you disentangle the surface productivity influence through remineralization of organic matter?
Using this delta 13C, using the calcium carbonate coarse fraction, and there is organic carbon record from the same core.
So calcium carbonate coarse fraction shows high productivity during the Holocene. So that time we could expect the phytoplankton will have a enriched delta 13C. So why can't be it's a remineralization of those phytoplankton which are buried in the sediment?
Sorry, I didn't get the second part. What? During the Holocene?
Your calcium carbonate percentage shows the high productivity during the interglacial period and the low productivity during the glacial period.
Yes.
So we do expect that when there is a high productivity, the carbon isotope of the primary productivity will enrich, right? So why can't your delta 13C of Bentic Forum, enriched Bentic Forum during interglacial period doesn't imprint the surface productivity? The remineralization of carbon comes from the surface productivity.
I will look into this. I'm not quite sure because I don't think at that depth there will be effect of productivity that much.
No, it's not a product. It's a remineralization of the surface phytoplanktons because those are the oxic waters, right?
Okay, I will look into that. I can't say anything for sure.
Okay. Okay.
Yeah, Nisha, okay, you can answer him later on. I mean, that's a good question. We can move ahead, Raju bhai.
Yeah, please go ahead. Someone introduce the rest of the speakers.
Okay. Now the next one is from Latika. Deep
Yeah.
water circulation in the Arabian Sea during the last glacial period, last glacial cycle. Please, Latika,
Yeah. Uh,
can you share your screen?
yeah, sure. I'm doing that. Yes. Can you see my presentation?
Yes. Yes.
Yeah, so good morning, everyone. My name is Latika. I work in National Center for Polar and Ocean Research as a researcher. And today I will talk on deep water circulation in the Arabian Sea during the last glacial cycle. And this is part of my PhD work, and this got recently published in Quaternary Science Reviews. As an introduction, I would like to talk about briefly on global thermohaline circulation. So this involves the formation and transport of deep water masses in North Atlantic and Southern Ocean to the entire global ocean. And this is a simple cartoon of thermohaline circulation where major water masses and their transport are indicated. And the black arrows represent the deep water masses like North Atlantic deep water and Antarctic bottom water, and the red arrow represents the surface water masses. So as a whole, it becomes a global conveyor belt. Now, why is this global thermohaline circulation so important? Because it helps in the transport and redistribution and distribution of heat, salt, and play a major role in the carbon storage capacity of the ocean, and thereby affects the global climate. So it will be interesting to know or understand what happened to the global thermohaline circulation in the geological past. Now, in the modern time, water masses are identified by hydrographic parameters like salinity and temperature, but when we have to study past changes, we need to take the help of proxy records. There are multiple proxies to study ocean circulation changes like del C13, neodymium isotope, cadmium calcium, etc. But here I will be talking on neodymium isotopes, and in the following slides I will explain why neodymium isotope is a promising tracer for ocean circulation and why it is a better proxy than biological proxies. So neodymium belong to the rare earth element group, and as any other trace elements, it has various sources to the ocean, like through rivers as dissolved and particulate ND, through winds as aeolian derived neodymium, and through hydrothermal processes. However, the studies have shown that hydrothermal contribution to the ocean is minimal. Now, there is another process known as boundary exchange process, through which the seawater along the boundary get affected by the neodymium transporter from the boundaries of the ocean. However, in the open ocean setting, the ND isotopic variability is mainly controlled by water mass mixing. Now, one particularly interesting thing about neodymium is that its residence time is 500 to 1,000 years, which is much less than the oceanic mixing time. So individual water masses will have individual ND isotopic values, like North Atlantic deep water will have more negative value, -14, Pacific will have a more positive value, like -2 to -4, and Indian Ocean will have a intermediate value, Indian Ocean water masses -8 to -9. Actually, ND isotope acts as a fingerprint of the water mass, we can say. Now, another point which I forgot to mention it here is that neodymium isotope doesn't get affected by any biological processes. So, unlike del 13C or cadmium calcium, ND isotope variability in ND isotope record represents the variability in water mass mixing. Now, we can measure neodymium in different archives like foraminiferal shell, fossil fish teeth, through bulk sediment leaching, and neodymium isotope is calculated through this formula: epsilon ND is equal to measured ratio 143 by 144 minus Chur value divided by Chur value. Chur is the quadratic uniform reservoir. Now, here I have taken an image from Tachikawa et al. 2017. As you can, this include all the available records from the global ocean. You can see that Indian Ocean sector is understudied, but on global thermohaline circulation perspective or global circulation perspective, Indian Ocean is an important area because it hosts the deep water masses, as it doesn't have its own deep water mass protection. And since it is away from the formation regions, any changes in the deep water masses are very well documented in northern Indian Ocean especially. So you can see there are few records in Bay of Bengal, but studies have shown that, earlier studies have shown that Bay of Bengal records are highly influenced by local changes. So we need to have a record which is affected by local changes in somewhere else. So keeping this in mind, we have selected a core from Arabian Sea away from the boundary in the open ocean setting from a water depth of 2,600 meters. Here I have shown all the water mass pathways, be it surface water mass like Red Sea water, Persian Gulf water, or the deep water masses as circumpolar deep water. You can see that to the Arabian Sea, please keep in mind, to the Arabian Sea, the circumpolar deep water mass travels through the western pathway. Now coming to the result, this is the ND isotopic record of Arabian Sea. We have measured two archives, foraminifera and bulk leach, and both show similar values. This shows the reliability of the data, and they shows glacial interglacial variability you can see in the ND isotopic record. This shows that there is a water mass source change. There is more negative values during interglacial periods, MIS1 and MIS5, and more positive values during glacial periods. So more negative value indicates more proportion of North Atlantic deep water, and more positive values indicate more proportion of Antarctic bottom water. Here I have tried to compare our data with all the existing data from Bay of Bengal, Equatorial Indian Ocean. Irrespective of the local changes, you can see that all the record shows a similar pattern, like interglacials have more negative value and glacials have more positive values. Now, since I already mentioned, Bay of Bengal records are highly affected by local changes. So from here on, I won't be discussing about Bay of Bengal. So let's focus on Arabian Sea and Equatorial Indian Ocean. Although they follow the similar glacial interglacial pattern, you can see there is a magnitude difference of almost 1 epsilon ND during the interglacial MIS1 and MIS5. So to explain this change in the magnitude between these two basins, in the Arabian Sea basin, we have proposed three mechanisms. One mechanism is that maybe Arabian Sea record is getting affected by the Arabian Sea water masses like Red Sea water, Persian Gulf water, etc. But these are surface water masses. To bring them to a deeper depth, physically it is not possible. So we can rule out this possibility. Now, second possibility, we thought that maybe when the circumpolar deep water travels through the western pathway, it get changed. The epsilon ND value get affected through the boundary exchange from Madagascar or Mascarene Basin. But you can see this is an RC1183 from South Atlantic. That record and Arabian Sea record are similar in magnitude as well as in pattern. So if any changes has happened through this through the transport, it should be these two records should not be similar. So we rule out that possibility also. Now the third possibility we have is to the Equatorial Indian Ocean, the water mass reaches through a central pathway, and to the Arabian Sea it reaches through the western pathway. So we propose that maybe through two different pathways, the circumpolar deep water reaching has different proportion of Antarctic bottom water and North Atlantic deep water. To look into that, what we did is we generated a temperature salinity diagram using the modern salinity and temperature values for station representing SK129CR2 and Arabian Sea core, and the temperature salinity.
Latika, please wrap it up.
Diagram interestingly shows that Arabian Sea water. Sorry.
Yes, we can hear you. Please wrap it up. Time is up.
Okay, yeah, just 2 minutes. So you can see that Arabian Sea water masses are more denser than the equatorial Indian Ocean water masses. So Antarctic bottom water is a more dense water mass. So we propose that the water mass reaching to the Arabian Sea has a more proportion of Antarctic bottom water compared to the circumpolar deep water reaching to the equatorial Indian Ocean. And we also try to quantify the percentage of Antarctic bottom water reaching to the both the basin, and we can see that during interglacial period MIS1 and MIS5, and this Arabian Sea has a almost 80% Antarctic bottom water, whereas equatorial Indian Ocean has 60%, while during glacial period, interestingly, all the basin has almost 95% of Antarctic bottom water. Why is it? Because during interglacial period, the study shows that North Atlantic deep water production is reduced or transport is reduced. So the only water mass existing is Antarctic bottom water, which occupies the entire northern Indian Ocean basin. So to summary, this is the first record of neodymium isotope, and it shows more negative values during glacials and more positive values during glacials, showing water mass source changes. And there is a epsilon ND value difference between equatorial Indian Ocean and Arabian Sea during interglacials, which is explained in terms of relative variation in the export of Antarctic bottom water and North Atlantic deep water. And this glacial interglacial change in the relative export and distribution of North Atlantic deep water and Antarctic bottom water has implications to the paleoredox condition of the water column, carbon sink capacity of the basin, and atmospheric carbon dioxide variability. Thank you.
Thank you, Latika. If anyone wants to have question.
Hello, Latika, this is Ramanan. Hello.
Hi.
Hello, I have one query. During especially the MIS5 time, you can see from the core SK129 CR02 to northern part of there is a huge difference in the values, especially epsilon this neodymium. So what is really representing this central equatorial was this ocean water not moving that side, or any other feature is there? I mean the Indian this deep water mass is there.
No, actually, the equatorial Indian Ocean SK129 CR2, the water mass is reaching through the central pathway. And you can see between Arabian Sea and equatorial Indian Ocean, there is a difference in MIS5, as you said. So we are proposing, what we are proposing is that to the western pathway, more Antarctic bottom water is reaching, and through the central pathway, compared to Arabian Sea, the proportion of Antarctic bottom water reaching is less. That is, more North Atlantic deep water is reaching.
So I'm asking the cause about why it is not moving towards northern side. Is it any reason behind that?
This Lakshadweep bridge is
Yeah,
so
okay,
the water
okay, I got it.
from equatorial Indian Ocean cannot pass to the Arabian Sea.
Okay, thank you.
Thank you, Latika. Thank you very much. It was really a nice presentation. Now we can move to the next one by Pragati Gautam. Antarctic circumpolar current strength variability along the Drake Passage and its influence on microbiota productivity distribution. Could you please share your presentation and start?
Yes, sir. So can you see my slide?
Yes.
Okay. So a very good morning to everyone present here. This is Pragati Gautam, master student from Indian Institute of Technology, Bhubaneswar. Going to talk about how Antarctic circumpolar current strength is variable along the Drake Passage, and it is influencing on microbiota productivity and its distribution. So starting with the introduction about the Antarctic circumpolar current, that it is the world's strongest oceanic current, and it is flowing clockwise direction around the Antarctic Peninsula, which is driven by strong westerly winds. And the strength of this current is variable along the Drake Passage, and along the Drake Passage during the glacial and interglacial period. However, McGave et al. Suggested that minimal changes occurred in ACC flow speed between last glacial and Holocene. With this, Lamy et al. Discussed about millennial scale variation in Drake Passage through flow using this sortable silt as its proxy. Also, the Wu et al. In 2021 explained that the ACC strength is variable along the Drake passage using sortable silt as its proxy, which results that higher sortable silts indicate the higher current strength during the interglacial period, whereas lower sortable silt indicating the reduced speed during the glacial period. Here we can see that how the sortable silt is higher during the interglacial period, where this sortable silt is low during the glacial periods. And this implies that the current strength is reflecting the sortable silt abundance. And but none of the studies have mentioned about the influence of Antarctic circumpolar current strength on microbiota during the glacial and interglacial period. Hence, to formulate this, we have chosen our study area right on the Drake Passage, and which is at a Chilean continental margin, that is 30 nautical miles southwest of the Chile coast, and the samples were taken from 2,100 meters of water depth. This Drake Passage is influencing by the Humboldt water current system and the Cape Horn current system also. Our study is done with an objective to understand the ACC strength variability in the Drake Passage and its influence on microbiota productivity and distribution. So for our study, we used two methods. One is for sedimentological analysis, where we have analyzed the grain size using the particle size analyzer. And the second is for identification of our microbiota, where we have washed our samples and studied the samples of greater than 125 micrometer under the stereo zoom microscope. Generally, radiolarynx and diatoms were studied by preparing smear slide because of their smaller size. But in this site, we have recorded them of size greater than 125 micrometer, possibly due to its nutrient level and productivity during the glacial period also. So coming to the results, since we don't have exact data, exact ages of our samples, so we have studied them with respect to the depth. Our grain size data that showing that the sands are much more as compared to that of silt, and where this sand is representing that they were either driven by the Chilean coast or due to the melting of glacier, whereas these clay are representing deep marine environment. As McGill et al. Proposed that sortable silts are used as a proxy to estimate the current strength. So in our samples also we find the same, and that the sortable silts were variable that are high during the higher current strength and vice versa. Where this interpretation was supported by the saying of Lamy et al. Also, that the current strengths are variable over the studied period. So our statistical data for grain size suggests that the coarser, mean size and poorly sorted and finely to nearly symmetrical skewed grains representing higher current strength, whereas this moderate to highly sorted and coarsely skewed represent the lower current strength. So this is about our microbiota analysis, where we have observed that the influence of ACC strength on microbiota. Here we see that at the gray bands, we see the lower sortable cells, which is showing the lower abundance of microbiota, and that lower abundance of microbiota also showing the lower current strength, and at this higher sortable cells area we see the higher productivity of forams during the higher current strength. On observing the species, we have found G. bouloides as a dominating during the higher current strength, which is high productivity indicating planktic species, and also we have found Neoglobopachiderma, which is a cold water adaptive species, as a dominating species during the weaker ACC strength, suggesting the glacial period. Along with this, we have also found Globocacidulina sp and Vilonis spp abundance during higher and lower current strengths. So these are few abundant planktic foraminifers. That this is Globigerina bouloides, this Neogloboquadrina pachyderma, and this is Neogloboquadrina incomte. So these are the few abundant benthic foraminifera of size. This scale showing 100 micrometer, where this is a Sebicidus sp. This its umbilical view, and this is its spiral view. With this Cacidulina sp, Globocacidulina sp, Melonis, and Uvigerina. So hence my study. About the study, I would like to conclude by saying that the higher the mean sortable silt reflecting the higher current strength during the interglacial period, whereas lower mean sortable silt representing the lower current strength. Also, ACC current is influencing the productivity of microbiota in the manner that the forums productivity is high during the higher current strength and low during the lower current strength. These are my conclusion references, and with this, a thank you to all.
Thank you, Pragati. Any question is there? Yes, Masood Kausar.
Hi, Pragati.
Hello, sir.
Yeah. This is really interesting to find this kind of correlation. But what may be the cause of such correlation, like high current intensity and high productivity? Is it something with nutrients coming more to the side, something like that?
Yes, we can say about nutrients also that when the during the interglacial period, when the current is flowing, so the supply of the nutrients is more for the these microbiotas to like grow. So. And saying about the sortables, that if the strength is high, the sediments supply is also more. And since we are taking it for 10 to 63 micrometer of size of sortable silt, so this yes, it is all about that.
Okay. Do you consider other factors, like several papers they mention that during interglacials, some wind circulation that bring sediments or dust particle from Peruvian region. So can that be a reason that you are getting high productivity during interglacials?
Sir, actually we are not now considering these factors, but maybe in a future study we will do for that also.
Yeah, please check on that, because
okay,
it will strengthen your discussion.
Thanks for the suggestion, sir.
So now we can move to the next presentation. Dr. Pratima Kesarkar is not there to present, so we'll go to move to the next one. Shubham Tripathi. Two-phase variability of denitrification and South Asian monsoon from marine isotope stages 18 to 28. Shubham, are you there? Shubham?
Latika, can you ask Shubham if he is around in NCPR?
We have received any mail from Shubham? You'll go for the next one, Rajibhai?
Yeah, it's fine. Please go ahead.
Sudhira R. Bhadra.
Yes, sir, I'm there.
Yeah, please, could you start your presentation? His presentation will be on
Yes,
a
sir.
significant shift in the upper water column structure of the Bay of Bengal post-mid-Pleistocene transition. Please, Sudhirji.
Oh, please.
Share your screen.
Good morning, everyone. I am Sudhir Bhadra. My presentation for the morning is a significant shift in the upper water column structure of the Bay of Bengal post mid-Pleistocene transition. So it's been quite some time that people are looking at dynamic changes in the dynamic condition of Indian monsoon beyond the last interglacial. And in the long-term record, mid-Pleistocene transition is a very important climatic phenomena that occurred that affected the global climate by changing the so-called 41 kiloyear Earth to 100 kiloyear Earth. So in order to know that on the Indian monsoon has affected its surrounding water masses in the different ways, and one of the parameters and the very unique with a very unique hydrodynamic condition is the Bay of Bengal. So Bay of Bengal experiences the seasonal changes in the different monsoons in the wind direction as well as the current direction. Also the precipitation minus evaporation changes is also very much during both the seasons. And the rainfall mostly is more concentrated in the northern part during the southwest monsoon, whereas it's concentrated in the southern part and the northeast monsoon. And as you can see, most of the Bay of Bengal riverine discharges here is more during the southern monsoon, southwest monsoon only, and so it says that the most of the precipitation occurs or the riverine influx that occurs during the southwest monsoon only. So knowing all this and this freshwater influx also changes the vertical structure of the Bay of Bengal by inputting low salinity and high temperature water on the Bay of Bengal. So to considering all this, I have selected my objective to understand the changes in the water column stratification during the mid-Pleistocene transition. For this study, I have used foraminifera as a proxy because of its ubiquitous and sensitiveness. And for the sample, we have used IODP samples, IODP 353U1446 location, the samples we have been used. And the samples have been processed following the standard protocol followed in our lab. And 5 to 15 specimens of Neodymium deuterate has been used for the isotopic study in the Rbmc facility in the PRL. Here we have taken the mixed layer and thermocline variability of salinity and temperature, and we can see that there is a strong thermocline here, and it's also there is a seasonal change. Mostly in the case of salinity, it is very prominent. So in order to the salinity changes, what can it result that if low salinity, very low salinity water during the summer monsoon season can create a low salinity cap and thereby increase the stratification. So there has been many studies, not many studies, like few studies in the Bay of Bengal only, like 3. And here Season Kumar et al, they have used a delta Deletino. That's the Deletino difference between surface dwelling foraminifera and thermocline dwelling foraminifera to know the stratification changes. And they have related to the salinity. And more difference means more fresher, that means low salinity water. And low salinity water, as I talked about, it will increase the stratification. Here, Naik and Naidu et al. Also applied the same delta 18 difference between rubber and deuterate to talk about the salinity and stratification changes in the younger dryas time. And similarly, Bolton et al. Have done this, taking the delta 18, and this has been done from the equatorial Indian Ocean, that's southern part of beyond southern Bay of Bengal. But all of these studies, they don't include the mid-Pleistocene transition, and we wanted to know how the mid-Pleistocene transition has altered the oceanography parameters and indirectly the monsoon. So we have taken delta 18 between deuterate and difference between deuterate and rubber as opposed to the other studies which they have taken between the surface dwelling foraminifera and deuterate. So these are some schematic diagrams so representing how it will be changing. So if strong summer monsoon is, so there will be a low salinity cap and shallow mixed layer and thermocline will be more and more stratification. So delta 18 will be high in that case. The difference will be high. And weak summer monsoon, so there will not be much terrestrial influx, so mixing will be enhanced and weak stratification, delta 18 will be low. And at the same time, strong winter monsoon, the convective mixing will be more and there will be weak stratification and delta 18 will be low. And if it is weak winter monsoon, then strong stratification will be there because low wind, no mixing, and delta 18 will be high. So both the scenarios are here. So here we have taken the delta 18 and we see that most of the time during the interstadial period throughout the record in general, the delta 18 is high, representing that more stratification during the interstadial period. But what we see a very interesting change is here that after mainly the 700 to 1050 is considered mid-Pleistocene transition. After the onset of mid-Pleistocene transition, the shift in glacial interglacial shift decreases to very large extent. It's like it's very minimum, and mostly and more minimum means less, even less after the mid-Pleistocene transition ends, like after 700 kiloyear. So there could be like two possibilities why this glacial interglacial shift is less. One is like weak summer monsoon during interstadial and strong winter monsoon during stadial. That way both will decrease the delta 18 and the difference will be less. Another scenario can be the strong summer monsoon during the interstadial and weak winter monsoon during the stadial and comparatively less weak summer monsoon during the stadial. That means the summer monsoon in general stayed strong but the winter monsoon stayed weak. So to know the difference, we have taken the mixed layer assemblage and thermocline assemblage of foraminifera. We have prepared by taking different foraminifera species, grouping into different assemblages. And we can see that here after specifically the 700 kilo or the mid-Pleistocene transition, there is an increase in general increase in the average thermocline assemblage. Thermocline assemblage increase means more thermocline dwelling foraminifera, that will be thermocline will be more deeper and stratification will be more. So we say that after the post MPT period, the strong summer monsoon during interstadial and compared to like weak winter monsoon during the stadial period have resulted in this delta 18 less difference between delta 18 glacial interglacial value, stadial interstadial value. So these are my inferences, which I already talked about. The first one is stronger stratification in the warm interstadial, comparatively weaker stratification during the cold stadials. And after the onset of mid-MPT, the summer monsoon standard and the winter monsoon weekend, which resulted decreased glacial interglacial shift in the delta. Thank you.
Thank you, Sudeep, for the nice presentation. Presentation is open for the question now.
Yeah. Hi, Sudhi. Yeah, it's a nice presentation. I have two questions out of curiosity. Okay. So number one is how are you planning to disentangle the temperature stratification and salinity stratification from the delta 18 difference between those two species?
Okay, sir. So the thing is that the temperature and salinity, I haven't distinguished that here. But when I'm talking about temperature salinity, the freshwater influx causes the temperature to increase as well as the salinity to decrease. Both cases result in the stratification. So we have only talked about that. As far we haven't differentiated between the salinity changes or temperature changes in this study at least.
Okay, another thing is how is the seasonal distribution of G. rubra and the dew tree in the Bay of Bengal? Is it annually available, or it's a sorry to just biased towards some period, summer or winter period?
I didn't get you properly. I forgot to mention that the G. rubra Deloitin has been taken from Clemens et al. 2021. Yeah, please go ahead.
Yeah, I want to know the seasonal productive variation of a G. rubra and the dew tree over the Bay of Bengal, modern day.
Okay, so modern day there has been sediment trap studies. Also, in my PhD, I have done the surface sample studies. The sediment trap studies, they show that the variability of rubber and deuterate in the seasonally also. So both of them are more abundant during the throughout most of the year. Rubber is mostly abundant throughout the year, and deuterate is also mostly abundant throughout the year. So the seasonal bias is less compared to whatever is.
So it's not a summer monsoon stratification. It's a yearly annual. I mean, it's a not.
It's annual statistics. Yes. We can't say that it's summer monsoon statistics, but to know that, I have in the result section I have mentioned that how it could be like cases of two things also, that strong summer monsoon and weak winter monsoon, or it can be both also.
Okay, thanks for the clarification.
Thank you, Sudhir. And
thank you, sir.
Is Shubham around? We tried to call him, but no answer. So, Rajiv bhai, can we wrap it up?
Yeah, Pawan, I think since he is not around, then it's fine. We are dot in time. We were supposed to finish by 12 and then...
Exactly 12.
Yes. So we can hand it over to, I mean, there is no more session afterwards. So if Dr. Binita is around, then...
Yes.
So thank you, Rajiv. Thank you, Pawan, for conducting the session so well. I am glad that two participants could not present. We have an interesting session in the afternoon, 1:30 poster session, and we have about 16 posters to be seen in that. So some very interesting data would be displayed. And so I thank you all who are here. I see Professor Kale here. Hello, sir. And all the participants, I thank you all for this wonderful morning and these lovely, interesting data. And I'm sure that the chats that were going on and the connects that you've made will really help you, in the coming researches and collaborations that you will build. And sir, Vishwas sir, would you want to say something? It would be really nice if you could say a few words to our participants.
No, just appreciate the work that the youngsters have done. This is a totally different field, I mean, because it is related to the reconstruction of climate on the basis of the offshore records. So I'm not from that field, but I learned many things, and I would like to congratulate all the presenters. Thank you very much. Yeah.
Thank you so much, sir. Thank you for motivating the young researchers. So we break down for now, and we meet in 1.5 hours. So the link would be open. You can still be there, but we'll stop the recording. And we would be here again at about 1:20 so that we can start the session on time. The moderators for the next session, which the poster session, that would be Earth surface processes and ocean in Quaternary. So both these are cut together, and moderators will be Dr. Praveen Mishra and Dr. Sunil Shukla. So we'll see each other after 1.5 hours. Till then, have a nice lunch. Bye-bye.
Thank you. Thank you all.